Imagine standing at the edge of the world, not metaphorically but literally. Wind screams past you at nearly 200 miles per hour, so violent that it feels like a living thing trying to push you off the earth entirely. The temperature is so cold that exposed skin freezes in minutes, that your breath becomes visible ice crystals before they fall, that your eyes water and the tears freeze to your cheeks. All around you, in every direction, stretches nothing but white, an endless, featureless expanse of ice and snow that extends for thousands of miles. This is Antarctica, the seventh continent, a place so remote and so hostile that for most of human history, we didn't even know exactly what was there. Antarctica is the most extreme environment on our planet. It's a continent almost entirely covered in ice, some of it over 3 miles thick. If all that ice melted tomorrow, sea levels around the world would rise by about 200 feet. Entire cities would disappear beneath the waves. But that's not the only reason Antarctica fascinates us. The coldest temperature ever recorded by humans was on this continent. In 1983, at a Soviet research station called Vostok, the thermometer dropped to minus 128.6 degrees Fahrenheit. That's so cold that carbon dioxide freezes out of the air. That's so cold that metal becomes brittle and shatters like glass. That's so cold that your lungs can be damaged just by breathing. For centuries, Antarctica was almost entirely unknown to us. Ancient map makers drew it on their charts as a vast, mysterious landmass at the bottom of the world, but no one knew what was really there. When explorers finally started venturing to Antarctica in the 1800s and early 1900s, what they found was a landscape of almost incomprehensible harshness. Some of them died there, some went mad from the isolation, others turned back, unable to endure the cold and the darkness and the crushing sense of being on a completely alien world. And yet for nearly 2 centuries we assumed we understood what Antarctica was: ice, wind, rock, and absolute sterility. A place where nothing lived, nothing grew, and nothing would ever change. We were spectacularly wrong. The story of what lies beneath Antarctica's ice is a story that wasn't uncovered by explorers or adventurers, but by scientists staring at data. In the 1960s and 1970s, researchers began using a new technology called airborne radar to map what lay beneath the Antarctic ice sheet. Radar works by sending radio waves down through the ice and measuring how long they take to bounce back. By analysing those bounces, scientists could create a kind of picture of what was underneath, and that's when they started noticing something deeply strange. The radio waves were bouncing back in ways that didn't match what they expected. In some areas, the pattern of reflection suggested that beneath miles and miles of solid ice, there was something completely different, something that conducted electricity differently, something that behaved in the data like liquid water. But that seemed impossible. How could water possibly exist in a liquid state under 2 miles of solid ice, in a place where the air temperature never rises above minus 50 degrees Fahrenheit? It defied everything we thought we knew about physics. Ice floats on water, yes, but only when there's a small temperature difference. Under the weight of 2 miles of ice, with the air above it so cold that it seemed to defy the very idea of liquid water existing, it should all be frozen solid. And yet, the data kept telling the same story. There wasn't just one pocket of liquid water beneath the ice. There were many, hundreds, potentially thousands of them. Subglacial lakes, they were called, lakes that exist in complete darkness, sealed away from the world by an impenetrable ceiling of ice. As scientists refined their measurements and their understanding of the data, they began to realize that these weren't tiny, insignificant pools. Some of them were enormous. Some were larger than entire mountain ranges, and the biggest one, the one that would eventually capture the imagination of the world, was Lake Vostok. Lake Vostok lies beneath the Russian research station called Vostok Station, located in the interior of Antarctica. This station isn't just in a cold place, it's in the coldest place that humans have ever deliberately built a structure to live in. It's so remote that in winter, when Antarctica turns toward the sun and the long darkness begins, the station becomes completely cut off from the rest of the world. Planes can't land there, supply missions can't reach it. The people who winter there, usually fewer than a dozen, are completely isolated until the Antarctic spring returns, months later. They live in buildings that are themselves buried under snow and ice, because the snow accumulates so quickly that structures need to be constantly elevated. Vostok Station sits on top of the ice sheet, at an elevation of about 11,500 feet, and the nearest other human settlement is over 500 miles away across open, featureless ice. Beneath Vostok Station, at a depth of about 2,300 meters, roughly 7,500 feet, or a mile and a half below the surface, there is Lake Vostok. The lake itself is enormous. It's roughly the same size as Lake Ontario, one of the Great Lakes. It's about 150 miles long and 30 miles wide, and there, in complete darkness, in water that's just barely above freezing, separated from the rest of the world by a seal of ice that's been unbroken for an estimated 15 to 25 million years, the lake has sat in silence and isolation for millions of years. That means that this lake existed long before modern humans. It existed before the Ice Age cycles that have defined the last few million years of Earth's climate. It existed when the continents were in different positions, when the oceans were warmer, when the world was a completely different place. And in all that time, the lake has been sealed off, cut off from any contact with the surface world, surrounded by ice sitting beneath the weight of an entire continent. When scientists first realized that Lake Vostok existed, they became obsessed with reaching it. This wasn't just scientific curiosity, though there was plenty of that. It was the possibility of what might exist within it. If liquid water could somehow survive beneath the ice, what else might be there? What could live in such an environment? A lake cut off from the rest of the world for millions of years would be like finding an alien planet right here on Earth. It would be a completely separate ecosystem, evolving in isolation, with no connection to the world above. What would life look like in such a place? What would have adapted to exist in total darkness, in near freezing water, under unimaginable pressure? The Russian scientists at Vostok Station decided they had to find out. They decided to drill down to the lake. This sounds simple enough, but in reality, it was one of the most ambitious engineering projects ever attempted in Antarctica. They started drilling in 1989, using a special hot water drilling technique that melted the ice as it went down. Day after day, month after month, year after year, they fed the drill deeper and deeper into the ice. The drilling was slow and difficult. In the extreme cold, equipment broke constantly. Parts had to be specially designed to function at temperatures where most materials become brittle. The drill hole itself had to be kept open by filling it with a special antifreeze mixture that wouldn't freeze solid. If the hole froze closed, everything would be lost. Years of work, millions of dollars invested, and the chance to reach the lake would vanish. By the early 2000s, they were getting close. The drill had penetrated more than 2,000 meters into the ice. Scientists could feel that they were approaching the lake. The drill readings were changing, the temperature was increasing as they got deeper, and they were running out of ice. But there was a problem. The Russian scientists weren't allowed to drill all the way through the ice to the lake. International treaties governing Antarctica, specifically the Antarctic Treaty System, have strict rules about what kind of research can be done on the continent. There are concerns about contaminating pristine environments. There are concerns about introducing bacteria and pollutants from the surface into a sealed ecosystem that's been isolated for millions of years. And there's a deeper concern too, the idea that we should preserve some places on Earth completely untouched, as a kind of global heritage and scientific preserve for future generations. So the drilling stopped at about 3,769 meters, about 12,370 feet, just 10 to 20 meters above the surface of Lake Vostok. The drill was so close you could almost feel it. The lake was almost within reach, but they couldn't quite make it. They took samples from the ice core that came up from the hole, ice that had been frozen in place just meters away from the lake's surface. And when they analysed those samples, when they looked at what they had managed to recover from that sealed environment, they found something astonishing. There was life in that ice. The samples that came up from the depths contained biological material, bacteria and other microorganisms that had come from Lake Vostok itself, trapped in the ice near the surface. These weren't modern contamination. These weren't organisms from the surface that had been carried down the drill hole. These were ancient microbes that had been living in the lake, had migrated upward through the ice, and had become frozen in place thousands of years ago. Life had found a way to exist in Lake Vostok. Life had adapted to darkness, to cold, to isolation, to an environment more extreme than almost anywhere else on Earth. And that discovery changed everything. It suggested that liquid water beneath Antarctica's ice wasn't sterile. It wasn't a dead zone. It was home to something. It was a living world hidden from us, sitting beneath the white silence of the continent for millions of years. The implications were staggering. If life could exist in Lake Vostok, then maybe it existed in the other subglacial lakes too. Maybe hundreds of these hidden lakes were teeming with microorganisms we'd never seen before. And if we wanted to understand what was down there, if we wanted to study these hidden worlds, we had to do it very carefully. We had to do it in a way that didn't destroy the very thing we were trying to study. In the years that followed, the international scientific community debated the best way to study Lake Vostok. How could they reach the lake without contaminating it? How could they understand what was living down there without destroying the ecosystem they were trying to explore? Various proposals were floated. Some scientists wanted to melt a hole and lower instruments into the lake itself. Others wanted to use more sophisticated drilling techniques that could minimize contamination. Some suggested that they should use ice-penetrating radar to analyze the lake's structure from above without ever touching it at all. The debates went on for years, with different countries and organizations pushing for different approaches. But in February of 2012, something happened that changed the debate entirely. The Russian drilling project reached the lake. After more than 20 years of drilling, after passing through 2,300 meters of ice, after overcoming countless technical and bureaucratic obstacles, the drill finally broke through into Lake Vostok. It happened suddenly. The drill dropped about 6 meters as it entered the water, and the pressure inside the borehole changed, indicating that they had reached the liquid lake beneath the ice. The Russians had done it. They had reached Lake Vostok. They had made contact with the hidden world beneath the ice. The moment the drill broke through, alarms started going off about potential contamination. The borehole was no longer sealed. Antifreeze and drilling fluid could theoretically flow down into the lake. Microorganisms from the surface could potentially enter the water. The international scientific community was both thrilled and horrified. They had finally reached the lake, but in doing so, they might have disrupted the very ecosystem they wanted to study. The Russians, however, argued that the contamination would be minimal, that the water in the borehole would quickly refreeze, and that the small amount of material that might enter the lake would be insignificant in a body of water so vast. Over the following years, more samples were collected from the borehole as it was drilled deeper into the lake itself. Scientists analysed the water, analysed the sediments, analysed every scrap of biological material they could extract. What they found was that the lake was indeed alive. It contained microorganisms, mostly bacteria, that had adapted to survive in this extreme environment. These weren't just a few stray microbes. There were thriving communities of them, living off chemical energy derived from the interactions between the rock, the ice, and the water. The lake had a food chain, albeit a strange one, based not on sunlight and photosynthesis like almost all life on Earth's surface, but on chemicals in the water and on the lake bottom. Some of the organisms they discovered were completely new to science. They had genetic signatures that didn't match anything that had been catalogued before. Scientists theorized that these microbes might have been evolving in isolation for millions of years, adapting to the unique conditions of the subglacial lake environment. They might represent a completely separate branch of life's family tree, isolated for so long that they've become fundamentally different from anything living on the surface. Every microorganism they found was a discovery. Every sample raised new questions about how life could exist in such conditions, and what that might tell us about life's possibilities elsewhere in the universe. Because here's the thing, if life can adapt to survive in Lake Vostok, in total darkness, in freezing water, in complete isolation, under unimaginable pressure, then maybe life can adapt to survive almost anywhere. Maybe those subglacial lakes aren't just interesting because they exist here on Earth. Maybe they're interesting because they show us what life might look like on places like Europa, one of Jupiter's moons, which is believed to have a vast ocean of liquid water beneath its icy surface, or Enceladus, one of Saturn's moons, which has recently been discovered to have liquid water geysers erupting from beneath its ice shell. The study of Lake Vostok and other subglacial lakes isn't just about understanding Antarctica, it's about understanding the possibilities for life in the universe itself. The discovery of life in Lake Vostok was, in a very real sense, the discovery of an alien world without having to leave Earth. It was a reminder that our planet still holds enormous secrets, that there are places on Earth that we barely understand, that there's still so much to discover and learn. It was also a humbling discovery. We thought we knew our planet. We thought we'd mapped everything important. We thought the extremes of Earth's environments were well understood, and then we looked beneath the ice and we found an entire world we didn't know existed, with life we'd never seen before, asking questions we'd never thought to ask. Antarctica, that white emptiness, that land of ice and wind and cold, suddenly seemed less empty. Beneath the surface, below the ice, in the darkness and silence, there was movement, there was life. There was a world as alien as anything we could imagine, and yet it was right here, all along, waiting to be discovered. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe to the Calm Archive and let me know in the comments where you're watching from and what time it is. I always check the comments, and it's fascinating to see people from all over the world. Anyway, back to what they found beneath the ice. When the Russian scientists first analysed the samples from Lake Vostok, when they first looked at the data coming back from that drill hole reaching down into the darkness, they had to sit with the reality of what they were discovering. This wasn't just an empty lake frozen beneath the ice. This wasn't just an interesting geological feature that had been sealed off for millions of years. This was a living system. This was an ecosystem that had evolved in complete isolation, that had adapted to conditions so extreme that virtually nothing on the surface of Earth experiences them. And the more they studied it, the more detailed the picture became. The lake's water is not pure ice melt. It contains dissolved minerals that have leached from the rock below, giving it a unique chemistry that supports the microbial life living within it. The lake bottom is covered in sediments, layers of material that have accumulated over millions of years. If you were to drill a core through those sediments, you would be reading the history of the lake layer by layer, going back through time. And somewhere in those layers is the story of when this lake was first sealed off by ice, when it was cut off from the rest of the world and forced to become self-sufficient. Scientists estimate that Lake Vostok has been sealed beneath the ice for somewhere between 15 and 25 million years. That means it's been isolated since the middle of the Tertiary period, back when the world was warmer, when Antarctica didn't look the way it does now. Over those millions of years, the microorganisms in the lake have been living, evolving, adapting to their unique environment. They've been developing unique biochemistries, unique ways of getting energy from their surroundings, unique strategies for survival. Some of them might be remarkably ancient, organisms that have remained essentially unchanged for millions of years because the environment they live in is so stable and unchanging. Others might be relatively recent descendants of those ancient microbes, having evolved to exploit slightly different niches within the lake. The bacteria that live in Lake Vostok seem to operate on principles quite different from most life on Earth's surface. They don't depend on sunlight. They don't have access to the vast biological communities that exist in oceans and on land. Instead, they seem to rely on chemosynthesis, a process where organisms use chemical energy rather than light energy to build their bodies and sustain themselves. The chemicals they use come from the rock below the lake, from interactions between the water and the minerals of the Earth's crust. There's sulfur in that water, and iron, and other elements that can be oxidized or reduced by bacteria to release energy. It's a form of life that exists at the very edge of what we consider life to be. Minimal, efficient, perfectly adapted to an environment that could support nothing else. What makes this even more remarkable is the pressure. The lake is so deep, and the ice above it is so heavy, that the pressure at the lake's surface is many times greater than the pressure we experience at sea level. The water molecules themselves are being squeezed from above by the weight of that ice. The bacteria living in this water have adapted to handle that pressure. Their cell membranes, their proteins, their entire biochemistry has been shaped by evolution to function under these extreme conditions. If you took a sample of Lake Vostok water and brought it to the surface, if you relieved the pressure, the microbes in it might actually die. They've become so perfectly adapted to their extreme environment that a return to normal conditions would be lethal to them. The temperature of the lake is another factor that's shaped the life within it. The water isn't as cold as the ice above it. It's warmed slightly by heat rising from the Earth's interior, but it's still only a few degrees above freezing. Life on Earth's surface experiences a much wider range of temperatures. We have organisms living in hot springs and geysers. We have organisms living in deserts where temperatures swing wildly between day and night. We have organisms living in tropical rainforests where it's always warm. But in Lake Vostok, the temperature barely changes. It's a stable, steady, very cold environment. The bacteria there have adapted to that cold. Their enzymes function at temperatures that would paralyze or slow down the enzymes in surface organisms, and yet Despite these extreme conditions, life thrives. Or perhaps thrives is too strong a word. Life survives. Life persists. Life finds a way to exist, even in a place that seems impossibly hostile. The microbial communities in Lake Vostok have found a niche, have adapted to fill it, and have been doing so, seemingly unchanged in many cases, for millions of years. In some ways, they're the most successful organisms on the planet. They've solved the problem of surviving in an environment that nothing else on Earth can survive in. They've created a stable ecosystem that doesn't depend on the rest of the world. They're completely self-contained, completely self-sufficient, completely isolated. This isolation is perhaps the most remarkable thing about Lake Vostok. For millions of years, this ecosystem has existed without any input from the rest of the planet. No new genetic material has entered from the surface. No sunlight has penetrated. No large organisms have arrived. No nutrients from the outside world have supplemented what the microbes can produce themselves. It's a completely closed system, in as much as such a thing can exist on Earth. And yet life has not only survived in this closed system, it appears to have evolved and diversified. There are multiple species of bacteria in Lake Vostok, each adapted to slightly different niches within the lake. Some live near the surface of the water, some in the middle depths, some on the lake bottom. Some are more abundant, some are rarer. There's a community here, a society of microbes, all dependent on each other in various ways. We're still learning what that community looks like. The drilling operations at Lake Vostok are still ongoing, though they have been intermittent due to the challenges of the environment and the delicate questions about contamination and preservation. Each new sample brings new information, new mysteries to solve. Scientists are studying the genetics of these microbes, trying to understand how they were related to bacteria on the surface, trying to trace their evolutionary history. They're studying the chemistry of the water, trying to understand how energy flows through this ecosystem. They're studying the sediments on the lake bottom, trying to read the history of the lake, trying to understand what it was like millions of years ago, back when it was first sealed off by the growing ice sheet above. But perhaps the most profound question that Lake Vostok raises isn't about the lake itself. It's about what it tells us about life's possibilities. If microorganisms can thrive in Lake Vostok, if they can survive for millions of years in complete darkness and isolation, in freezing water beneath miles of ice, then what does that tell us about where else life might exist? In our solar system alone, there are places that might have conditions similar to Lake Vostok. Europa, the moon of Jupiter, is believed to have a vast ocean of liquid water beneath its icy shell. If such an ocean exists, if it's been sealed off beneath the ice for billions of years, might it be home to life? Might it have developed its own ecosystem, its own community of organisms adapted to those extreme conditions? Or consider Enceladus, one of Saturn's moons. Recent observations have shown that Enceladus has geysers that eject water into space from an ocean believed to exist beneath its icy surface. The composition of that water, the heat that drives it, the chemistry, all of it seems potentially compatible with life. If Enceladus has an ocean beneath its ice, might it have microorganisms like those in Lake Vostok living on chemical energy rather than sunlight, adapted to survival in extreme conditions? We don't know. But Lake Vostok teaches us that such conditions can support life. Lake Vostok shows us that life is more resilient, more adaptable, more creative than we might have imagined. Looking at Lake Vostok, scientists have become convinced that life in the universe might be far more common than we once thought. We used to think that life required certain specific conditions. It needed liquid water, yes, that seems to be crucial, but it didn't necessarily need to be on the surface of a planet. It didn't need sunlight, it didn't need oxygen, it didn't need a magnetic field to protect it from radiation. It didn't need any of the things that make Earth's surface such a hospitable place for life. It just needed liquid water and the presence of chemical energy to be tapped. That's a far lower bar than we once thought. That opens up the possibility of life in places we haven't even discovered yet, in places that seem impossible, in places that nobody would have thought to look. And that's perhaps the greatest gift that Lake Vostok has given us. Not just the knowledge that there's a hidden ecosystem beneath the Antarctic ice, not just the discovery of strange new microorganisms adapted to extreme conditions, but the expansion of our sense of what's possible, the reminder that life is not fragile. Life is not confined to a narrow band of conditions around our own planet. Life is adaptive, resilient, and willing to thrive in places that seem impossibly hostile. And if that's true here on Earth, in Lake Vostok, If life can find a way to exist in that sealed, frozen world, then what does it mean for the rest of the universe? What does it mean for all the other worlds out there? All the other places where liquid water might exist? All the other sealed environments where life might have been quietly evolving for millions or billions of years, unknown and undiscovered, waiting for us to finally look in the right direction? The story of Lake Vostok is still being written. The drilling continues, the samples keep coming, the mysteries keep accumulating. Every answer leads to new questions. Every discovery reveals something we didn't know before. But one thing is certain. Beneath the ice of Antarctica, in a lake that's been hidden from the world for millions of years, life has found a way. Life persists. Life adapts. Life thrives in conditions that should be impossible. And that, perhaps more than anything else, is what makes Lake Vostok not just a scientific curiosity, but a testament to the power and the possibility of life itself. To truly understand the mystery of subglacial lakes, we must first step back and imagine what Antarctica was like long before it became the frozen, desolate continent we know today. 34 million years ago, the Earth was a different world entirely. The Antarctic continent, which today conjures images of endless white expanses and temperatures that plunge far below zero, was a lush and vibrant landscape. Imagine walking across what's now Antarctica and seeing forests of southern beech trees reaching toward a warmer sky. These forests were dense and thriving, full of life adapted to a temperate climate. Rivers flowed across the land, carving pathways through the earth, carrying water from highlands to lowlands in patterns that have long since been erased. Lakes dotted the landscape, shimmering under a sun that warmed the surface enough for water to exist in its liquid state without the pressure of miles of ice holding it down. The air was different too. It carried warmth. Birds flew overhead. Animals moved through the forests and along the riverbanks. When you stood on the ground in ancient Antarctica, you would have felt soil beneath your feet, seen plants and vegetation all around you, and experienced a climate that, while cooler than the tropics, was nothing like the harsh, unforgiving environment that Antarctica has become. This transformation did not happen overnight. The changes that turned Antarctica from a green and living continent into the frozen realm we observe today took place over millions of years. During what scientists call the Eocene epoch, the continents were positioned differently on the globe. Antarctica at that time was not isolated at the South Pole. It was connected to other landmasses. South America was much closer, and Australia remained linked in ways that would later change. The climate of the entire planet was warmer. The atmosphere contained higher concentrations of carbon dioxide. The oceans were warmer. Everything contributed to a world where the far southern continent could support forests and life. But gradually, the position of the continents shifted. This continental drift, driven by the slow movement of tectonic plates beneath the Earth's surface, eventually isolated Antarctica. As it drifted further south and moved closer to the South Pole, the global climate began to cool. This cooling trend was gradual but relentless. Over millions of years, the average temperature of Antarctica decreased. The winters grew longer and colder. The summers, once warm enough to support extensive forests, became shorter and less warm. The ice began to accumulate. This process, known as glaciation, started slowly. Patches of ice formed in the highest elevations, where it was always cold enough for snow to remain on the ground year-round. As the climate continued to cool, these patches expanded. More and more of the landscape became covered in snow and ice. The ice was not static, it moved. Under its own weight, it began to flow downhill, carving out valleys and reshaping the landscape. As the ice accumulated and grew thicker, it created more ice, which grew even heavier, pressing down on the land beneath it. Over millions of years, this accumulation of ice transformed into massive ice sheets that covered the entire continent. Today, the Antarctic ice sheet is almost incomprehensibly vast. When we measure its volume in cubic kilometers, the numbers are so large that they lose their meaning in our minds. 26.5 million cubic kilometers of ice. Imagine attempting to visualize that quantity. If we could somehow melt all of this ice and pour it into the world's oceans, sea levels would rise by approximately 200 feet. Entire coastal cities would disappear beneath the waves. Small island nations would vanish completely. The geography of the world as we know it would be radically redrawn. This single continent contains enough frozen water to fundamentally alter the surface of our planet. The weight of this ice is equally staggering. Ice is heavy, and the Antarctic ice sheet is so heavy that it actually pushes the bedrock of the continent downward. In many regions of Antarctica, the weight of the ice has forced the continent's bedrock below sea level. The surface of the land itself has been depressed by the tremendous burden resting upon it. If the ice was somehow to suddenly disappear, the land would begin to rebound, rising upward over a period of thousands of years as it was relieved of this immense pressure. This process, called isostatic rebound, shows us just how profoundly the ice has reshaped Antarctica at the most fundamental level. Within this vast ice sheet lies a frozen world of almost surreal extremes. The temperatures at the surface are so cold that they have become nearly incomprehensible to those of us who live in warmer climates. The coldest temperature ever reliably recorded on Earth was measured in Antarctica, at Vostok Station, where the thermometer dropped to negative 89 degrees Celsius, or approximately negative 128 degrees Fahrenheit. On many days throughout the Antarctic interior, temperatures hover around negative 50 to negative 60 degrees Celsius. The air is so cold that moisture in the atmosphere freezes immediately, creating suspended ice crystals that catch the light in strange and beautiful ways. The wind across the ice sheet is relentless and bitter, carrying nothing but ice particles. There are no trees to break the wind, no hills to redirect it. It flows freely across the white landscape, unobstructed. The ice itself is not simple frozen water sitting on top of the ground. It is a complex and dynamic material that changes with depth. At the surface, where snow falls and accumulates, the snow is relatively light and fluffy. As new snow falls on top of it year after year, the weight of the overlying snow gradually compresses the lower layers. The snow becomes denser, harder, more compact. The air spaces between the ice crystals diminish. Over time, hundreds or thousands of years of accumulated snow becomes compressed into what we call glacial ice. This ice is denser than the original snow, clearer in many places and more solid. As we descend deeper into the ice sheet, the pressure increases. The ice becomes even more densely packed. Air bubbles that were once present become compressed smaller and smaller. The ice from thousands of years ago is literally being squeezed by the weight of all the ice above it. And yet, beneath all of this weight, something extraordinary happens. At the base of the ice sheet, in the zone where the ice meets the bedrock below, an unexpected discovery awaits. Despite the extreme cold at the surface, despite temperatures that seem hostile to any liquid water, there are places where water exists in liquid form. This hidden water is perhaps one of the most astonishing features of the Antarctic continent, and understanding how it comes to exist requires us to think carefully about the physics of ice and water. The existence of liquid water at the base of the ice sheet is the result of two competing factors working in concert. The first factor is the immense pressure of the ice above. When we think of how ice forms, we usually imagine water freezing at its normal melting point of 0 degrees Celsius or 32 degrees Fahrenheit. But the melting point of ice is not actually a constant. It changes based on the pressure applied to the ice. This property is known as pressure melting point depression. When ice is under tremendous pressure, its melting point drops. It becomes possible for ice to melt at temperatures that would normally be cold enough to keep it frozen solid. At the base of the Antarctic ice sheet, the weight of the overlying ice creates pressures that are almost as extreme as the surface temperatures. The ice is so heavy that it presses down with crushing force. The melting point of ice at these depths drops significantly below the normal freezing point of water. In some places, the ice at the base could be at a temperature as low as negative 15 or negative 20 degrees Celsius, and yet it can exist in a partially melted state, producing liquid water at the ice bedrock interface. This is possible only because of the pressure. Were that same ice to be removed and placed at the surface, where the pressure is much lower, the water would refreeze immediately. The second factor contributing to liquid water at the base of the ice sheet is heat from the Earth itself. Beneath the Antarctic continent, in the layers of rock and stone that make up the crust of the planet, there is heat. This heat comes from the interior of the Earth. The core and mantle of our planet are extremely hot. This heat is constantly being conducted outward, flowing from the hot interior toward the cooler surface. In most places on Earth, this geothermal heat is small and easily ignored. But over vast timescales and across large areas, it has real effects. At the base of the ice sheet, this geothermal heat flux, though small, is a crucial source of warmth. It slowly, gradually, relentlessly warms the ice and the bedrock above it. The combination of these two factors creates the conditions necessary for liquid water to exist in this most unlikely place. The pressure reduces the melting point of ice so that it can remain solid only in a supercooled state, or remain partially liquid at temperatures that would otherwise freeze water solid. The geothermal heat provides warming. The result is liquid water at the base of the ice sheet, at the interface between the ice above and the bedrock below. This water exists in a zone that is often only a few meters thick, a thin film of liquid between two solids. It is water that has never seen sunlight, water that has never been in contact with the open air, water that exists in total and absolute darkness, squeezed between ice and stone. The existence of this basal water is crucial to understanding how glaciers and ice sheets behave. Water is much more slippery than ice. The presence of water at the base of a glacier or ice sheet allows the ice to slide more easily across the bedrock beneath it. The water acts as a lubricant, reducing friction and allowing the massive weight of ice to move. This basal sliding is the primary way that glaciers move toward the ocean. The water at the base of the Antarctic ice sheet, despite its existence in such an extreme environment, plays a fundamental role in how the ice sheet flows and changes. But the hidden water of Antarctica is not limited to a thin film of liquid at the base of the ice sheet. Scientists, using radar and other remote sensing technologies that can penetrate the ice and image what lies beneath, have made a discovery that is perhaps even more remarkable. Beneath the ice, an entire network of lakes exists. These are not small and insignificant features. They are substantial bodies of water ranging from a few kilometers across to lakes that are dozens of kilometers long. Over 400 such lakes have been identified and catalogued beneath the Antarctic ice. 400 lakes, completely hidden from the surface, lying in total darkness under miles of ice. These subglacial lakes form where the basal water collects in depressions in the bedrock, or where the water is channeled into reservoirs by the shape of the underlying landscape. Each lake fills with water derived from the melting of ice at the glacier bedrock interface. The water that fills these lakes is ancient. It has been isolated for millions of years in some cases, locked away in darkness with no connection to the atmosphere or to the ocean. The water is under tremendous pressure from the weight of the ice above, yet it remains liquid. The water is cold, hovering just below the normal freezing point of water at the surface, kept in its liquid state by the pressure and the warmth of geothermal heat. The darkness is absolute. No sunlight has reached these waters since they became isolated beneath the ice millions of years ago. The different subglacial lakes have very different characteristics. Some of them are completely isolated and sealed. These lakes have been separated from the rest of the hydrological system for so long that they have become entirely enclosed ecosystems. The most famous of these is Lake Vostok, one of the largest subglacial lakes beneath Antarctica. Lake Vostok is approximately 250 kilometers long and 50 kilometers wide. It is deeper than many of the world's largest surface lakes. This massive lake lies about 3,800 meters below the surface of the ice. It has been sealed beneath the ice for between 15 and 34 million years, cut off completely from the rest of the world. In that time, the water has been in total isolation. No new material from the surface has entered the lake. No water from the lake has left and entered another system. It is a closed system, locked away in darkness and cold, yet liquid and filled with heat from the Earth's interior. Other subglacial lakes are not isolated in this way. Instead, they are connected to each other and to a larger network of flowing water beneath the ice. Scientists have discovered that beneath Antarctica exists what might be described as a hidden hydrological system, a network of lakes and rivers and streams that flows beneath the ice, completely invisible from the surface. Water flows from lake to lake through channels in the ice and bedrock. Some of these channels connect to each other, creating a complex system of flowing water. The direction of flow is determined by the slope of the bedrock beneath the ice and the pressure gradients in the water itself. Water flows from areas of higher pressure to areas of lower pressure, just as it does in any hydrological system. This hidden network of lakes and rivers is dynamic and changing. Unlike the completely isolated lakes, these systems are not static. Water moves through them. The lakes fill and drain. Some lakes periodically release their water suddenly, in events known as subglacial outburst floods. When a lake drains catastrophically, millions of cubic meters of water rush through the channels beneath the ice, carving new paths, eroding the bedrock and creating tremendous forces as they flow toward the ocean. These drainage events are so large and sudden that they can be detected from the surface. The ice sheet above responds to the sudden loss of water. It subsides, sinking down to fill the void left behind. Scientists observing the surface of the ice from satellites can see it rise and fall as water drains from lakes beneath the ice and then gradually refills them as the cycle begins again. The existence of these interconnected lakes creates a dynamic and constantly changing system beneath the ice. We tend to think of Antarctica as static and unchanging, an eternal frozen wasteland where nothing moves and nothing changes. But beneath the surface, liquid water is flowing. Lakes are filling and draining. The water is moving through channels and passages driven by pressure and gravity, flowing steadily toward the ocean. The ice sheet itself is responding to these changes in water beneath it. The bedrock is being shaped and reshaped by the flowing water. An entire world of hydrological activity is occurring in darkness, concealed from our observation until we develop the technology to peer beneath the ice. Imagine, for a moment, what it would be like to descend through the ice sheet. You would pass through layers of ice of different ages, each layer representing years or decades or centuries of accumulated snow and ice. As you went deeper, the pressure around you would increase. The ice would become denser, harder, more intensely compressed. The temperature would gradually increase as you approached the base of the ice sheet. It would never become warm in any conventional sense, but the increase in temperature toward the bottom would be noticeable. You would pass through frozen layers containing air bubbles from the ancient atmosphere, bubbles of air that had not been disturbed in hundreds of thousands of years. These bubbles, when scientists have studied them, have revealed the composition of the atmosphere at the time the snow fell, providing a record of climate and atmospheric conditions stretching back hundreds of thousands of years. As you neared the base of the ice sheet, you would begin to encounter water. First, perhaps the ice would become slicker, more slippery. Water, in small quantities, would begin to appear within the ice itself. The transition from solid ice to the water-filled basal zone would not be sharp and sudden, but rather a gradual shift. And then, if you were fortunate, you might reach one of the subglacial lakes. You would emerge from beneath miles of overlying ice into a dark body of water. The water would be cold enough that normal human physiology could not tolerate immersion in it for more than a few minutes. The pressure would be immense. If you were to somehow remain at the surface of this hidden lake without protective equipment, you would feel the weight of the atmosphere above you, the weight of the ice pressing down. The darkness would be total. Even with the most powerful flashlight, the water would appear to fade away into blackness after a short distance. The silence would be profound. There would be no wind, no waves driven by wind, no sound of moving ice or flowing water. Just profound, absolute silence. The water itself would be pristine in a way that no water on the surface of the Earth is pristine. It would contain no algae, no visible living things, no sediment or dissolved organic matter from the surface world. It would be isolated water, unique water, unchanged for millions of years. And yet, as scientists would later discover when they finally obtained samples of water from Lake Vostok and other subglacial lakes, life exists in these waters. Despite the total isolation, the absolute darkness, the cold, the pressure, and the apparent hostility of the environment, living organisms have been found in the subglacial lakes. This discovery would fundamentally change our understanding of where life can exist on Earth, and would open up new possibilities for understanding the potential for life in the most extreme environments of the solar system. The geological story of Antarctica is a story of dramatic transformation over millions of years. From a lush and forested continent to a frozen, icy world, the change was gradual but total. The water that once flowed openly across the surface in rivers and lakes that was visible and accessible and teeming with life has been driven underground, sealed beneath ice and trapped in darkness. And yet, the water persists. It continues to flow. It continues to exist as a liquid, warmed by the heat of the Earth's interior and kept liquid by the pressure of the ice above. It has become a hidden world, a secret realm that exists unseen and unknown for millions of years, until the tools of modern science finally allowed us to detect its presence and begin to uncover its secrets. This hidden world of subglacial lakes and rivers represents one of the last great unexplored regions on our planet, a vast frontier that remains mysterious and largely unknown, lying beneath the ice in the coldest, most inhospitable place on Earth. In the depths of the Antarctic continent, beneath layers of ice so thick that the pressure alone would crush most living things, There exists a body of water so isolated, so untouched by the modern world, that it exists almost in another dimension. This is Lake Vostok, and what we've learned about it in recent decades has fundamentally changed the way we think about life itself, and where it might exist in places we once considered completely inhospitable. Lake Vostok isn't a small body of water. Imagine a lake so vast that it stretches for 160 miles in one direction. Picture in your mind a water body that spans 30 miles wide at its broadest point. Now imagine that this entire massive lake is sealed away under 2.3 miles of solid ice. That's 2.3 miles, more than 12,000 feet of frozen water sitting on top of this subglacial wonder. The lake's depth varies, but in some places it plunges down more than 2,600 feet, deeper than many submarine canyons on the ocean floor. When scientists first began to comprehend the true dimensions of Lake Vostok, they realized they were looking at something truly staggering. It is the 6th largest lake in the world by volume. The 6th largest. Not a small research pond hidden beneath the ice, not an underground spring or a minor aquifer. We're talking about a body of water whose volume could rival Lake Ontario on the Earth's surface. Yet virtually no one knows it exists. When you think about Lake Ontario, you think about a place teeming with life, with fishing boats, with swimmers on summer days, with seagulls wheeling overhead. Lake Vostok exists in absolute, total, permanent darkness. The conditions within Lake Vostok are so extreme that for many decades scientists simply assumed nothing could possibly live there. The water temperature hovers around -3 degrees Celsius. That's about 27 degrees Fahrenheit. Not quite freezing at the top of the water column, but close enough that the margin between liquid and solid is frighteningly thin. The only reason the water doesn't freeze solid is the enormous pressure. Remember those 2.3 miles of ice above? The weight of that ice creates a pressure of approximately 350 atmospheres. 350 times the atmospheric pressure you experience right now, at this moment, in your normal life. That tremendous pressure pushes down on the water with such force that it depresses the freezing point. It's the same principle that allows ice skaters to glide across frozen surfaces. The pressure from the blade can briefly melt the ice underneath. In Lake Vostok, this pressure is sustained, relentless, and constant. It is what keeps the water liquid in an environment that would otherwise freeze it solid. The water receives no sunlight whatsoever. No photons have reached this lake for millions of years. There is no photosynthesis. There are no plants producing oxygen. There are no algae blooms. There is no light in any form that organisms on Earth's surface would recognize. The darkness is absolute and eternal. Yet surprisingly, the water of Lake Vostok is far from empty of dissolved gases. In fact, Lake Vostok contains something extraordinary. It is supersaturated with oxygen. The concentration of dissolved oxygen in Lake Vostok is approximately 50 times higher than you would find in typical lakes on the Earth's surface. This seems paradoxical. How can a body of water hidden beneath miles of ice contain such abundant oxygen when no photosynthetic organisms exist to produce it? The answer lies in the ice itself. Oxygen from the atmosphere above has been slowly, over millions of years, incorporated into the ice sheet. As snow falls and accumulates year after year, century after century, millennia after millennia, the oxygen in that snow becomes trapped. When the ice sheet moves, when it flows and deforms under its own weight, when pressure and temperature conditions change, that trapped oxygen very slowly dissolves into the water below. It's an incredibly slow process, a process that unfolds across geological timescales. But across millions of years, a significant amount of oxygen accumulates. Beyond oxygen, the water chemistry of Lake Vostok may contain nitrogen and other gases that have been similarly trapped and incorporated. The exact composition is something scientists are still working to understand, as direct sampling remains extraordinarily difficult. Taking samples from Lake Vostok without contaminating this pristine environment is perhaps one of the greatest technical challenges of modern science. The age of Lake Vostok is a fascinating question, with multiple answers depending on what aspect you're asking about. The lake basin itself, the geological depression that holds the water, has been in existence for an extremely long time. But the current ice sheet that covers it is much younger. Estimates suggest that the current isolation of Lake Vostok, the period during which it has been sealed beneath the ice without contact with the atmosphere, dates back approximately 15 to 25 million years. That's millions of years of complete isolation. No outside influence, no new species entering from the surface, no escape routes for any creatures living within. 15 to 25 million years is an almost incomprehensible stretch of time. The earliest human ancestors hadn't yet walked on the African savanna. The continents were in slightly different positions. The climate of the world was dramatically different. And all that time, this lake has been sealed. However, the water itself is likely much younger than that. This is where things become even more intriguing. Scientists believe that the water in Lake Vostok is likely only about 13,000 years old. Or rather, the bulk of the current water has been cycling through the lake for roughly 13,000 years. How is this possible if the lake has been sealed for 15 to 25 million years? The answer lies in the slow, melting and refreezing cycles that occur beneath the ice sheet. The rock beneath the lake isn't as cold as the ice above. There's geothermal heat emanating from within the earth. This heat causes some of the ice at the base of the sheet to melt. That meltwater can percolate through the sediments and rock, becoming part of Lake Vostok. Meanwhile, water at the edges of the lake can refreeze, becoming incorporated back into the ice sheet. This slow, patient churning of water means that while the lake basin has been sealed for millions of years, the actual water molecules currently in the lake are far younger. It's like a slow, ancient recycling system, renewing itself at a glacial pace across tens of thousands of years. The question that captivated scientists for decades was simple but profound. Could anything live in Lake Vostok? The question seemed almost rhetorical. What could possibly survive in complete darkness, in water just barely above freezing under crushing pressure, with no obvious food source? How could an ecosystem possibly establish itself under such conditions? Conventional wisdom suggested that nothing could. Life, as we understand it, needs certain things. Most organisms need sunlight or chemical energy from the surface. They need temperatures that allow biological processes to occur. They need access to organic matter, food. Lake Vostok seemed to offer almost none of these things. It existed in a state that seemed fundamentally incompatible with life as we knew it. Yet scientists, being curious by nature, began to wonder. They had learned, over the preceding decades, that life on Earth was far more resilient than anyone had previously imagined. In the 1970s, scientists had discovered entire ecosystems around hydrothermal vents on the ocean floor, in complete darkness, powered not by sunlight, but by chemical energy from the Earth itself. These chemosynthetic ecosystems, found around deep-sea vents, represented a paradigm shift. If life could thrive in the deep ocean around vents, perhaps life could thrive in other dark, extreme environments. Perhaps Lake Vostok was not quite the sterile tomb scientists had imagined. The water chemistry of Lake Vostok offered some possibilities. The lake sits atop rock and sediment. If there were geothermal energy sources, and there almost certainly are, chemical reactions could be occurring in the water and sediments. Minerals dissolved in the water, iron, manganese, and other elements could serve as an alternative to photosynthesis. Chemosynthetic bacteria might potentially use these chemical energy sources to survive. Simple organisms, perhaps, but organisms nonetheless. The pressure and the cold water, while extreme, might not actually be insurmountable barriers. After all, the depths of the ocean experience similar or even greater pressures, and life flourishes there. Organisms can adapt to cold. Organisms can adapt to pressure. But could they adapt to all of these things simultaneously, in isolation, with minimal food sources, in complete darkness for millions of years? That was the question that kept scientists up at night. It was a question that seemed almost impossible to answer without actually getting to the lake and studying what was there. In the meantime, scientists used the tools available to them. Radar surveys from satellites and aircraft mapped the ice surface. Complex computer models used the gravity and magnetic signatures of the rock and water beneath to help understand the shape and dimensions of the lake. Seismic surveys provided additional data, and out of these surveys came one of the most intriguing discoveries. The lake appears to contain an island. Nobody has ever seen this island. It exists in permanent unbroken darkness beneath more than 12,000 feet of ice. Yet the radar and other geophysical data suggest strongly that there is a landmass rising from the lake floor and protruding upward into the water column. How long is it? What does it look like? Does it have any special significance? Nobody knows. The island remains one of the great unsolved mysteries of Lake Vostok. If organisms exist in the lake, The underwater island might be a crucial part of their ecosystem. It might provide a surface for biofilms to form. It might alter water circulation patterns and create chemical gradients that organisms could exploit. Or it might be entirely sterile, like everything else in that deep, dark world. The very existence of this unseen island, persisting in the darkness for millions of years, strikes at something profound about our planet. There are places on Earth that have never been seen by human eyes. There are features, potential ecosystems, that exist in isolation so complete that they might as well be on another planet. The island in Lake Vostok reminds us how much of our own world remains unknown. If you're still awake and enjoying this journey into the frozen depths of Antarctica, consider subscribing to the Calm Archive. A like really does help more people find these videos when they can't sleep. We create these narratives specifically for moments like this, when your mind needs something to settle on, something fascinating but soothing, something that takes you far from the stresses of daily life and deposits you in the wonder of scientific discovery. Your subscription helps us continue making content for people seeking calm and knowledge. Now let's get back to what lies beneath the ice, to the questions that have puzzled scientists and inspired new expeditions into this alien world hidden beneath our own planet. The question of life in Lake Vostok gained particular urgency in the 1990s and 2000s, as technology improved and scientists began to seriously contemplate actually reaching the lake. This wasn't a casual scientific curiosity. If life did exist in Lake Vostok, it would represent something truly revolutionary in our understanding of biology. It would demonstrate that life could exist in what we call extremophile conditions, extreme in every conceivable way, with no connection to the surface world, no exchange with the atmosphere, no relationship to the sun. It would suggest that life might exist in the subsurface oceans of Europa, one of Jupiter's moons, which scientists believe might harbour a liquid water ocean beneath its icy crust. It would change the way we search for life beyond Earth. It would expand the possibilities of the universe in ways we could barely comprehend. The scientific debate became intense. Some researchers proposed that chemosynthetic organisms could indeed exist in Lake Vostok, using dissolved minerals and chemical reactions as their energy source. Others were more skeptical, arguing that the isolation was simply too extreme, the conditions too hostile. The only way to settle the debate was to get actual samples from the lake. But accessing Lake Vostok was extraordinarily difficult. The ice sheet is more than 2 miles thick. Drilling down to the lake would require years of sustained effort. The ice is moving, flowing slowly across the landscape, so maintaining a borehole is challenging. And there was the critical issue of contamination. Any drilling fluid or equipment that scientists used could potentially introduce bacteria from the surface world into this pristine environment. The question of how to avoid contaminating Lake Vostok while sampling it became a major focus of scientific planning. Different nations undertook drilling projects at Lake Vostok. Russian scientists, working at Vostok Station, made the most progress. They drilled down through nearly the entire ice sheet, approaching the lake but stopping just short of breaching into it, fearing contamination. The cores they extracted told stories written in ice, bubbles of ancient atmosphere, dust from volcanic eruptions, chemical signatures of the climate over hundreds of thousands of years. But the cores also showed what was at the very bottom: water. Presumably the pristine, isolated water of Lake Vostok itself. American and other international teams also contributed research, deploying increasingly sophisticated methods to study the lake without opening it. Radio echo sounding mapped the lake's contours with remarkable precision. Gravity measurements helped determine the distribution of water and rock beneath the ice. Electromagnetic surveys probed the conductivity of the water and sediments. Slowly, a picture emerged of a vast subglacial lake with complex internal structures, with variations in depth and water chemistry, with a mysterious underwater island with conditions that seemed both hostile and surprisingly rich in possibilities. The dissolved oxygen that accumulates in Lake Vostok remained a major clue in this puzzle. That oxygen had to go somewhere. If nothing in the lake was using it, if no organisms were respiring and converting that oxygen back into carbon dioxide, then the oxygen would continue to accumulate indefinitely. But could oxygen really accumulate indefinitely? Or was something in the lake, something alive, breathing that oxygen, using it to power the fundamental processes of life? The question hung in the darkness above the unseen water, in the minds of scientists who had devoted their careers to understanding this subglacial world. The water of Lake Vostok is also characterized by unique density and thermal properties. Because it's so cold, and because of the dissolved gases and minerals within it, the water layers might not be uniformly mixed. There could be stratification, with denser water at the bottom and lighter water toward the top. This stratification could create distinct environmental zones. Some zones might be more conducive to life than others. An organism perfectly adapted to the conditions of the bottom waters, with their particular chemistry and pressure, might not survive higher up. Conversely, organisms that evolve near the surface of the lake might develop different characteristics. The lake could harbour multiple species, each adapted to their particular niche, their particular depth and water chemistry. Or it could be that the entire lake is utterly sterile, a vast body of water that has existed in geological isolation so long that life never became established within it. The sediments at the bottom of Lake Vostok would also be of tremendous interest to scientists. If organisms have lived in the lake, their remains would accumulate in the sediment. Fossils, shells, organic molecules, the evidence of life would be preserved in the accumulated layers of sediment laid down over millions of years. A core sample from the lake bottom would potentially read like a history book, telling the story of the lake's life, if life exists there. The sediments might contain diatoms, the silica shells of single-celled algae preserved in the silt. They might contain bacteria, frozen in time as the sediments accumulated. Or the sediments might be barren, containing only minerals and inorganic matter, silent testimony to a lake untouched by biology. The rock beneath Lake Vostok is another crucial element of this story. The thermal energy emanating from within the Earth, from the radioactive decay of elements deep within the planet, provides heat to the rocks below the lake. This heat could drive chemical reactions. It could create an energy gradient that organisms could potentially exploit. Hot water rising from below could mix with the cold lake water, creating zones of intermediate temperature where chemical reactions would proceed at different rates. These chemical reactions could produce compounds that microorganisms could use as an energy source. In essence, the rock beneath Lake Vostok could function as a kind of biological battery, providing the power source for life itself. The ecosystem of the deep ocean around hydrothermal vents operates in much the same way. Bacteria oxidize hydrogen sulfide and other chemical compounds, releasing energy that they use to grow and reproduce. Larger organisms feed on these bacteria. Complex ecosystems build themselves on this foundation of chemosynthesis. Could something similar be occurring in Lake Vostok? Could there be a hidden ecosystem, invisible to us, operating on chemical energy released from the Earth's interior, persisting in the darkness for millions of years? The possibility tantalized scientists. The more they learned about extremophiles, about life thriving in conditions previously thought to be incompatible with biology, the more plausible it seemed that Lake Vostok might indeed harbour life. Even if that life was simple, even if it was just bacteria or single-celled organisms, it would revolutionize our understanding of where life can exist. It would expand the boundaries of the biosphere, the zone of the Earth where living things can be found, and it would have profound implications for the search for life beyond Earth. If life could exist in Lake Vostok, in complete isolation, in crushing pressure, in darkness and cold, then perhaps life could exist on Europa, orbiting Jupiter. Perhaps it could exist beneath the ice of Enceladus, one of Saturn's moons. Perhaps it could exist in places we haven't even discovered yet, in oceans and lakes on worlds far from the sun. The isolation of Lake Vostok, its position as a sealed world within our world, made it the perfect analogue for these distant possibilities. The human stories surrounding Lake Vostok are equally compelling. Russian scientists have maintained the Vostok Station for decades, enduring the Antarctic cold, the darkness of winter, the isolation from the rest of humanity, all in service of scientific discovery. The station sits directly above Lake Vostok, built on the ice that seals the water beneath. The researchers working there are among the most remote people on Earth. They live in one of the harshest environments imaginable, yet they do so willingly, driven by curiosity about the hidden lake beneath their feet. The drilling project at Vostok Station has been one of the most ambitious scientific undertakings of recent decades. Drilling down through ice requires incredible precision and patience. The drill must be kept clean to avoid contamination. The borehole itself must be managed carefully as the ice moves and deforms. Year after year, the drill bit descended, penetrating deeper into the ice sheet, getting closer to the lake. The closest the Russians came to actually breaching into Lake Vostok was in 2006, when they stopped just meters short of the water surface. They have since resumed drilling, and the question of whether and when and how to finally sample the lake remains an active area of scientific planning and debate. The technology required to reach the lake, to sample it without contamination, and to preserve those samples is constantly being refined. Researchers are developing special sterilization protocols, sealed sampling devices, and ways to analyze the water without introducing foreign material. The prospect of finally accessing Lake Vostok, of being the first humans to see the water and study its contents, remains one of the great challenges and great prizes of modern science. It is a challenge that will require international cooperation, advanced technology, careful planning, and tremendous dedication. But the potential discoveries make it worth the effort. The possibility of finding life, of understanding how organisms can exist in extreme isolation, of expanding our knowledge of the conditions under which life can flourish. These possibilities drive the scientific community forward. Lake Vostok remains one of Earth's great mysteries, a hidden world waiting beneath the ice, a challenge to our understanding of life itself, and a reminder that our planet still holds secrets we are only beginning to uncover. The lake represents both the limits of our knowledge and the endless possibilities of scientific discovery. In its darkness, beneath miles of ice, it waits, patient and eternal, for the day when human curiosity will finally breach its frozen seal. As we move deeper into our journey beneath the Antarctic ice, we arrive at one of the most patient and deliberate scientific endeavours ever undertaken. The story of reaching Lake Vostok is not one of sudden discovery or dramatic breakthrough. Instead, it is a narrative of careful, methodical work spanning decades, a slow descent through frozen layers, an exploration measured not in days or months, but in years and decades of persistent effort. This is the story of the drilling, and it begins not with the lake itself, but with what scientists sought to find in the ice above it. In 1989, researchers at the Soviet Vostok Station, now Russian, now located in one of the coldest and most remote places on Earth, began an ambitious project. They wanted to drill downward through the Antarctic ice sheet, extracting ice cores as they went. An ice core is not merely a cylinder of frozen water, it is something far more precious, a time capsule. Each layer of ice, compressed year after year, century after century, holds within it the air from ancient atmospheres. When snow falls and accumulates, it traps tiny air bubbles in its crystalline structure. These bubbles preserve the exact composition of the atmosphere from the moment that snow fell. Sometimes thousands of years in the past, the Russians understood that by drilling down and extracting these cores, they would gain access to a continuous record of Earth's climate reaching back through the millennia. The drilling began methodically. Down they went, season after season, removing core after core, each one a precious archive of frozen time. The work was painstaking. The ice at the surface was relatively young, perhaps thousands of years old. But as the drilling continued, the teams were working with ice that fell as snow when humans were still discovering agriculture, when they were building the first cities, when civilizations were learning to read and write. Deeper still, the ice became older, tens of thousands of years old, then hundreds of thousands. Each meter drilled represented thousands of years of climatic history. The ice cores that emerged from the Vostok borehole revealed something extraordinary. They contained 420,000 years of Earth's climate history compressed into layers of ice. Scientists could read this history by analyzing the ice itself and the bubbles trapped within it. The isotope ratios in the ice told them about past temperatures. The composition of the trapped air told them about atmospheric carbon dioxide levels, methane concentrations, and other greenhouse gases from hundreds of thousands of years ago. They could see the patterns, the natural cycles of glacial periods and warmer interglacial periods that had characterized Earth's climate for millions of years. Embedded in these cores were signatures of dramatic events. Volcanic eruptions, ancient and long forgotten, had left layers of ash and dust in the ice. Massive storms from thousands of years ago had deposited their dust into the atmosphere, which had then settled and become part of the ice. The cores recorded temperature swings, the advance and retreat of ice ages, the slow oscillations of Earth's climate system through hundreds of thousands of years. This was one of the most important climate discoveries ever made. Not a single moment of revelation, but a slow, layered accumulation of knowledge, as one core after another emerged from the borehole and was analysed. But as the Russians continued to drill deeper, the purpose of the project began to shift subtly. The ice cores were important, certainly, but the drilling team realised they were approaching something else, something that existed not in the frozen ice above, but in the unfrozen water below. They were approaching Lake Vostok, the vast body of water sealed beneath the ice for millions of years. The question began to form in the minds of scientists around the world: should they drill into the lake itself? This question sparked one of the most intense debates in the history of modern science. It was not a debate about whether Lake Vostok existed. By this point, seismic evidence and radar imagery had confirmed its existence. It was a debate about ethics, about responsibility, about whether humanity had the right to breach the seal on an environment that had been isolated from the surface world for at least 15 million years, possibly much longer. The concern was contamination. If the drill pierced directly into the lake, what would happen? The borehole itself would provide a pathway from the surface to the lake's pristine waters. Drilling fluid, a necessary lubricant and coolant in the drilling process, would flow downward. Surface bacteria, microbes that existed in abundance in the atmosphere and on human equipment, might be carried downward. Modern microorganisms from the 21st century would be introduced into an ancient ecosystem that had evolved in complete isolation from the rest of the planet. Scientists from around the world argued passionately about the morality and wisdom of such contamination. Environmental organizations raised concerns. Biologists worried about contaminating an irreplaceable natural laboratory. Some argued that such contamination could destroy or alter any native microbial ecosystem that might exist in the lake, making it impossible to ever truly understand what had lived there in its pristine state. Others countered that the benefits of direct scientific study might outweigh these concerns. The debate continued, back and forth, year after year, as the drill continued its slow descent. The Russian scientists, listening to these concerns and recognizing the legitimacy of the environmental and scientific arguments, made a creative decision. They would not drill directly into the lake. Instead, they would employ a clever technique that would allow them to obtain a sample of the lake water without directly contaminating the lake itself. The method was elegant in its simplicity and ingenuity. As the drill bit approached the surface of the lake, as the borehole came within perhaps 10 or 20 meters of the water below, the Russians would stop drilling. They would leave a small gap between the bottom of the borehole and the surface of the lake water. In this configuration, pressure would naturally build. The weight of all that ice above, pressing down on the borehole, would create a pressure difference between the water-filled borehole and the lake itself below. This pressure difference would push the pristine lake water upward through this small gap, filling the lower portion of the borehole. Once the borehole was filled with lake water, that water would freeze during the Antarctic winter. The cold would transform it into solid ice, just like the ice above it. Then, in the next drilling season, scientists could carefully drill into this frozen lake water, recovering samples that were genuinely from Lake Vostok, while the actual lake beneath remained sealed, unpierced, uncontaminated. It was a solution that satisfied both the desire for scientific discovery and the ethical concerns about environmental preservation. It was a compromise that showed scientific humility, an acknowledgement that there were some environments on Earth that deserved to remain pristine, that the most valuable study of such environments might come not from direct intrusion, but from careful, respectful extraction of samples at their boundary. For many years, the drill continued its descent. The work continued at a pace dictated by the limitations of the ice itself, by the equipment available, by the harsh Antarctic climate that allowed only a few months of work each year before the station was locked in winter darkness. It continued at a pace that demanded patience, persistence, and an almost meditative acceptance of the slowness of the work itself. Scientists trained and retired. Equipment was maintained and occasionally replaced. The borehole grew deeper year after year, penetrating further into the ice, approaching the ancient water that waited below. And then, after more than 2 decades of drilling, the moment arrived. On February 5th, 2012, after 23 years of work since the project began in 1989, the drill reached the surface of Lake Vostok. The borehole penetrated to a depth of 3,769 meters, that is 12,366 feet, or nearly 2.34 miles, through the solid ice. At this depth, the pressure was immense, and then the waiting water made its presence known. Lake water, responding to the pressure differential, rushed upward through the small gap between the drill and the lake surface. It was a dramatic moment after so many years of patient waiting. A sudden movement, a sudden inflow of water that had been sealed away undisturbed for millions of years. The water flowed up the borehole, filling it as it rose, and then, as the Antarctic winter set in, it froze. By the time the drilling season ended, the water that had rushed up from the lake had transformed into solid ice, preserving a sample of the lake's contents in a form that could be studied and analysed in the seasons to come. The next drilling season, the scientists returned to the borehole. Carefully, with the same patience and precision that had characterised the entire project, they drilled into the frozen lake water that had accumulated during the winter. They extracted samples, ice cores that were not ancient ice from Earth's atmosphere, but rather frozen water from a living ecosystem that had been sealed away from the rest of the planet since before modern humans walked the Earth. And in those samples they found something that took the project beyond the realm of climate science and into the realm of biology and the origins of life itself. The frozen water from Lake Vostok contained DNA. This was not a complete surprise, theoretically. Scientists had anticipated that if life existed in the lake, it would be microbial, bacteria or archaea, or other single-celled organisms that could survive in extreme conditions, in complete darkness, under enormous pressure, in water that had never been exposed to sunlight. But the presence of actual DNA, extracted from actual samples, was different from theoretical possibility. It was confirmation. It was reality. The researchers found thousands of different DNA sequences in the lake water samples. Some of these sequences matched known bacteria, organisms that scientists had already identified and catalogued and studied. This was reassuring in a sense. It suggested that the sequencing and identification methods were working correctly, that they were capturing and identifying real biological material. But other DNA sequences matched nothing in any biological database. These were organisms that had no known relatives, no obvious match to anything that had ever been identified and described by modern science. This raised a profound possibility. Were these new forms of life, organisms that had evolved in isolation in Lake Vostok, cut off from the rest of the planet, developing their own unique evolutionary path? Or were they variants of known organisms that had simply drifted far enough from their known relatives that they no longer showed clear genetic similarity? The question remained open, and it remains open still. The discovery of microbial life in Lake Vostok had implications far beyond Antarctica. If life could exist in the extreme environment of a subglacial lake, in complete darkness under enormous pressure, in conditions that seemed, on the surface, to be utterly hostile to biological existence, then what did that tell us about life's capacity to persist in extreme environments? What did it tell us about the possibility of life on other worlds? Scientists began to imagine other places in the universe where similar conditions might exist. Jupiter's moon. Europa has a subsurface ocean beneath a thick ice shell, perhaps not so different fundamentally from Lake Vostok. Saturn's moon Enceladus has hydrothermal vents on its ocean floor, again suggesting an environment that, while more extreme than Earth, might still harbour life. If life could evolve in Lake Vostok's darkness and isolation, perhaps life could also exist in the darkness and isolation of an alien ocean beneath a frozen moon in the outer solar system. The drilling program continued after 2012. Over subsequent years, additional boreholes were drilled to different locations of the lake. Further samples were extracted, more DNA sequences were analysed. The picture that emerged was of a diverse microbial ecosystem, adapted to its extreme environment, living on chemical energy provided by geological processes rather than on light energy from the sun. The entire endeavour, from the initial decision to drill in 1989 through the first breakthrough sample in 2012 and beyond, represents something important about scientific practice. It represents patience. It represents the ability to commit to a single project over decades, to accept that some questions cannot be answered quickly, that some environments require slow, careful, respectful exploration. It represents international cooperation in the midst of the Cold War's aftermath, scientists from different nations working together toward a common goal. And it represents a kind of humble curiosity, a desire to know, balanced with respect for the environments being studied. As you listen to this narrative, as you imagine the slow descent of the drill through the ice, as you imagine the water rushing up the borehole when the surface of the lake was finally reached, Try to embrace that same sense of patient curiosity. Try to imagine the dedication it takes to pursue a single scientific question for more than 2 decades. Let the slowness of the work, the methodical nature of scientific discovery, calm your mind as you drift towards sleep. The scientists who drilled those boreholes were themselves engaged in a meditative practice, a slow, deliberate engagement with a mystery that would take most of a lifetime to unfold. And in the answer to that mystery, in the discovery of life in the deep, they found something profound about the nature of existence itself. Imagine for a moment the quiet persistence of life, not the loud, vibrant life we see on the surface of our planet, the roaring of animals, the rustle of leaves, the bustle of human activity. Instead, imagine life that asks for nothing but the gentlest of conditions, life that doesn't need sunlight or air, or the warmth of the surface sun, life that exists in perfect stillness, in absolute darkness, in the cold that would shatter most things we know. This is the reality scientists discovered when they finally looked beneath the ice of Antarctica, and what they found would change how we think about life itself. The first real glimpse into this hidden world came from Lake Vostok, though not in the way we might have expected. When researchers finally began to analyze the samples they extracted from that lake more than 2 miles beneath the ice, they didn't rush to dramatic conclusions. Instead, they worked carefully, methodically, examining particle by particle what had been sealed away in that water for millions of years. And in those samples they found something remarkable: bacterial DNA. Not fossilized remains from ancient times, but actual genetic material from living organisms. Some of these bacteria appeared to be species never before catalogued by science. Organisms that had evolved in complete isolation from the rest of the world, adapted perfectly to their lightless, frozen environment. What struck researchers most was the composition of these microbes. Many of them appeared to be thermophiles, organisms that love heat and thrive in warm conditions. This discovery raised a fascinating question. Why would heat-loving bacteria exist in a lake that is locked beneath 2 miles of ice? The answer pointed to something happening far below the surface of the lake itself. At the bottom of Vostok, beneath the water, there appeared to be geothermal vents. These are fissures in the Earth's crust where heat from the planet's interior escapes, the same kind of vents that create hot springs in Iceland or power the volcanic systems around the Pacific Ring of Fire. In this case, these vents were warming the very bottom of the subglacial lake, creating small pockets of relative warmth in an otherwise frozen world. It was in these zones that the thermophilic bacteria had made their home, feeding on the heat energy that came from deep within the Earth itself. The discovery of bacterial DNA in Vostok samples was intriguing, but it raised a persistent question in the minds of scientists. Were these organisms still alive, or were they fossils, ancient DNA preserved perfectly in the frozen environment? The samples had been exposed to potential contamination during the drilling process, and there was no clear evidence of metabolic activity. It was a tantalizing mystery, but one that couldn't be solved with the samples from Vostok alone. Scientists knew they needed something more definitive. They needed to drill into a subglacial lake, extract water and sediment, and confirm with absolute certainty that living, active microorganisms were present. This is where the story took a turn towards solid scientific fact. In 2013, an American research team called the WISARD Project, which stands for Willands Ice Stream Subglacial Access Research Drilling, accomplished what many thought would be impossible. They successfully drilled into Lake Willands, a much smaller and shallower subglacial lake beneath the West Antarctic ice sheet. Lake Willands is only about 2,000 feet beneath the surface, which is still an enormous depth, but it presented fewer challenges than the deep, pressure-filled environment of Lake Vostok. What made the WISARD project remarkable wasn't just that they drilled into the lake, but how they did it. They developed ultra-clean drilling methods, working with extraordinary care to ensure that no microbes from the surface world could contaminate their samples. The drill itself was sterilized. The protocols were meticulous. Every step of the process was designed to answer a single question: what living things are actually in this lake? When the first samples of water came up from Lake Willands, researchers rushed them to their analysis equipment. What they found was unambiguous. There were living microbes in the water, not DNA fragments or fossil remnants, but active, reproducing, metabolically functioning cells. These organisms were alive. They were consuming nutrients and energy. They were growing, they were dividing and creating new generations of themselves. It was a confirmation that moved beyond hypothesis into demonstrable fact. In a lake sealed beneath hundreds of meters of ice, cut off from the surface world for millions of years, life had not only survived but thrived. The confirmation sent waves through the scientific community. It meant that the subglacial lakes of Antarctica weren't just ancient curiosities, they were functioning ecosystems. There was life down there, right now. At this moment, as we rest here in the quiet, microbes are swimming and dividing in the darkness beneath Antarctica. But the question that naturally emerged was more profound. How do these organisms survive? This brings us to one of the most elegant solutions nature has ever produced. We are accustomed to thinking about life on Earth as being fundamentally dependent on the sun. Plants use photosynthesis to convert sunlight into chemical energy. Animals eat the plants, or eat other animals that eat plants, creating an endless chain of energy flowing downward from the sun. But in the subglacial lakes, there is no sun. There are no plants. There is absolute darkness that has persisted for millions of years. So what energy source sustains these organisms? The answer is chemosynthesis. Instead of using light energy, these microbes harvest chemical energy from the minerals in the bedrock around them. Iron, sulfur, manganese, and other elements present in the rocks undergo chemical reactions, and these organisms have evolved the remarkable ability to tap into those reactions, extracting energy the way a solar panel extracts energy from sunlight. It's a process that requires no light, no organic nutrients from above, just the steady, reliable presence of minerals and water. Some of these microbes feed on organic carbon that was trapped in sediments millions of years ago. Remember that Antarctica wasn't always frozen. Millions of years in the past, much of Antarctica was warm, covered with forests and vegetation. When the continent froze over, organic matter from those ancient ecosystems became sealed in the rocks and sediments beneath the ice. These subglacial microbes have access to that ancient preserved organic matter. They feed on the ghosts of a warmer world, sustenance from an environment that no longer exists on the surface, but persists intact in the sealed chambers deep below the ice. This chemosynthetic life is not unique to Antarctica. Scientists have found similar organisms thriving in some of the harshest environments on Earth. In the volcanic vents at the bottom of the ocean, in the acidic hot springs of Yellowstone, in deep underground aquifers completely cut off from the surface world, there are communities of organisms that sustain themselves purely through chemistry. They don't need sunlight. They don't need air. They don't need the familiar conditions that support most life on our planet's surface. These organisms are called extremophils, a word that literally means lovers of extremes. They thrive where other life cannot exist. They are the testament to the remarkable adaptability of life, to its ability to find a way in conditions that seem utterly hostile to existence. And now we know that beneath the Antarctic ice, extremophils have their own empire, their own kingdoms, their own ecosystems that have been evolving in isolation for millions of years. In 2018, another milestone in subglacial exploration was reached when scientists drilled into Lake Mercer, another of Antarctica's hidden lakes. The Wizard team and their colleagues repeated their careful, meticulous process, and they extracted water and sediment from this additional lake. What they found was not just living microbes, but something more surprising still. In the sediment, they discovered the remains of tiny animals. These weren't microbes, these were actual multicellular creatures. Crustaceans, tiny relatives of the shrimp and crabs we know from the ocean. Tardigrades, those remarkable water bears that have become famous in recent years for their ability to survive almost anything. These specimens found in Lake Mercer were not alive when they were discovered. They were dead. They were fossils, or more precisely, the preserved remains of creatures that had lived and died at some point in the past. But their presence raised a profound question. If the remains of these small animals are there now, sealed in the sediment, then at some point in the past, these creatures must have been alive in Lake Mercer, living, feeding, moving through the water in the darkness. The implications of this discovery are quietly profound. It suggests that the subglacial environment is not just inhabited by single-celled organisms, but that it can support small multicellular life. Crustaceans require more energy than bacteria. They need to move, to hunt, to maintain the complex processes of a larger body. If they lived in Lake Mercer at some point, it means the environment was able to sustain them. It means there was enough energy in the system, enough resources, enough stability. The discovery of these dead creatures doesn't tell us whether they still live there now. The specimens found were preserved in sediment, which means they accumulated there over time, perhaps over thousands or millions of years. But their presence is evidence that life in the subglacial lakes is not limited to the microscopic scale. It's not just bacteria surviving in a chemical darkness. There is a complexity here, a diversity of life that we are only beginning to understand. As scientists continue to study these extremophils in their frozen world, patterns begin to emerge. These organisms, whether they are bacteria or the remnants of small animals, share certain characteristics. They are slow. Their metabolism is slow. Their growth is slow. Their reproduction is slow. This is not a sign of suffering, but of efficiency. In a world where energy is precious and hard to obtain, slowness is an adaptation. It's a way of stretching scarce resources across the longest possible time. A single generation of these organisms might take months or years to complete its cycle, whereas a bacterium in a warm environment might divide every 20 minutes. But this slowness means they don't wear out. They don't exhaust themselves. They persist. In a dark, cold world sealed from all change for millions of years, persistence is the ultimate survival strategy. These organisms have perfected it. They have become the masters of stillness and patience. The extremophiles of Antarctica are teaching us something profound about the nature of life itself. We often think of life as requiring specific, narrow conditions. We imagine that life needs warmth and light and oxygen, and a constant supply of fresh nutrients. The extremophils prove us wrong. Life is more flexible, more adaptable, more relentless than we give it credit for. It finds a way. It doesn't just barely survive in extreme conditions. It thrives. It evolves and diversifies and creates complex ecosystems in environments that we would once have dismissed as completely lifeless. This is not a story about life struggling against hostile conditions. It's a story about life simply being itself, finding the rules of whatever environment it finds itself in, and then mastering those rules. As we think about these organisms now, in this moment of calm reflection, there's something almost meditative about their existence. They live in a world of perfect stability. There are no seasons beneath the Antarctic ice. There are no day and night cycles. The temperature never changes. The pressure never varies. The environment once established persists, unchanging, eternal. To us on the surface, this sounds like a prison. We thrive on change, on stimulation, on novelty. But to these organisms, it's paradise. It's a world where the rules are clear and constant, where they can focus simply on the fundamental act of existing, of persisting, of slowly, steadily continuing to be. But the story of subglacial life in Antarctica is not merely about understanding our own planet. It is a story with implications that reach far beyond Earth. Because if life can exist in such extreme conditions here, sealed beneath miles of ice, deriving energy from chemistry rather than sunlight, then the universe might be far more alive than we ever imagined. Consider Jupiter's moon, Europa. Deep beneath its icy crust, beneath a shell of ice many miles thick, there is a liquid ocean. We know this from the way Europa's gravity behaves, from the subtle signals we can measure from space. If there is an ocean under that ice, it's reasonable to wonder whether there are also vents in the ocean floor, whether there are minerals that could provide chemical energy, whether the conditions might be suitable for chemosynthetic life. If subglacial life exists here, why not there? Why not in the oceans beneath the ice of other moons and planets throughout our solar system? Saturn's moon Enceladus gives us even more direct evidence of such possibilities. Enceladus has geysers. We've seen them in images from the Cassini spacecraft, water fountains shooting up from the icy surface into the vacuum of space. The water is coming from an ocean beneath the ice, and the fact that it's coming out means there's activity down there. There are forces at work. There is heat. There are chemical reactions. The conditions that we've found support life in Antarctica might very well be present beneath the ice of Enceladus. Scientists who study the potential for life on other worlds often speak of places like Enceladus and Europa with a kind of wonder, not because we've found life there yet, but because the conditions seem so suitable. We look at these moons now with the knowledge that we have from Antarctica, and we see them differently. We see them not as barren, frozen wastelands, but as potential oases. We see them as places where life might hide, patiently persisting in the darkness, just as it does in the subglacial lakes of our own planet. The study of extremophiles and subglacial ecosystems has become one of the most important fields in astrobiology, the science that explores the possibility of life beyond Earth. Every discovery we make in the frozen lakes of Antarctica informs how we think about the potential for life on other worlds. Every organism we find thriving in impossible conditions expands the boundaries of where life might exist. When we drill into these lakes and find life, we're not just learning about Antarctica. We are learning about the universe, about the remarkable adaptability and persistence of life, about the incredible range of conditions under which existence is possible. The extremophiles beneath Antarctica are like a gift, a kind of cosmic reminder. They teach us that life is not fragile. Life is not dependent on any single set of conditions. Life is resourceful. Life is patient. Life finds a way, and that gives us hope, doesn't it? In a universe that can seem vast and empty and indifferent, the knowledge that life not only exists but thrives in conditions we would have once thought impossible is a source of quiet comfort. It suggests that life is not rare. It suggests that wherever conditions allow, life will emerge. It suggests that we might not be alone in this universe, that life might be hiding in places we haven't even thought to look yet, persisting patiently in the darkness of distant worlds, just as it does in the deep, still waters beneath the Antarctic ice. As you rest here in the quiet, you might let your mind wander down into those dark lakes, those sealed chambers beneath miles of ice. Imagine the profound stillness of it. Imagine the gentle persistence of life in the darkness. These organisms don't struggle, they don't rush. They simply continue, moment after moment, generation after generation, slowly, steadily, patiently. There is a kind of peace in that image, a kind of profound calm in the knowledge that life, in its infinite adaptability, has found a way to persist even in the most inhospitable places. Life continues, life endures, life thrives. And in that continuation, in that endurance, there is a kind of reassurance. If the Calm Archive has become part of your bedtime routine, I'd love it if you shared this video with someone who might need it tonight, and hit that subscribe button if you haven't already. Now, where were we? Deep in the darkness of those Antarctic lakes where life quietly persists, moment after moment in the cold and the stillness. Let that image settle into your mind as you drift towards sleep. Let the quiet persistence of those hidden organisms guide you toward rest. The world continues to turn. Life continues to exist in all its remarkable forms, and for now you can let all of that go and simply rest. When scientists first began mapping the subglacial lakes beneath Antarctica, they realized they were looking at far more than isolated pools of trapped water. What emerged from their research was nothing short of a revelation. An entire hidden hydrological system operating silently beneath the ice sheet, a vast and intricate network that rivals any river system on the surface. Today, we know that over 400 subglacial lakes exist beneath Antarctica, and rather than being independent pockets of water, they are connected to each other through an elaborate system of rivers and streams that flow unseen through channels in the bedrock below. These aren't small seeps or minor trickles. These are genuine rivers of water, some quite substantial in their flow, moving beneath the weight of nearly 2 miles of ice. When you imagine the landscape beneath Antarctica's ice sheet, it's helpful to think of it not as a uniform frozen block, but as a complex terrain of valleys and ridges carved by ancient processes, much like the land beneath any ocean or sea. The bedrock beneath the ice is not smooth. It has topography, mountains and valleys, plateaus and depressions, and where there is topography, water flows. Just as water on the surface of the Earth seeks the lowest points, following gravity and the contours of the land, subglacial water does exactly the same thing beneath the ice. It moves along the bedrock following gravity, carving pathways through ancient rock that no human has ever seen, will perhaps never see, yet continues its eternal work of flow and erosion in absolute darkness. The discovery of these subglacial rivers came as scientists mapped the terrain beneath the ice, using various technologies. Radar surveys, particularly ice-penetrating radar, allowed researchers to see through the ice and identify not just the water bodies themselves, but the channels through which water moves. They found that water flows from one lake to another, creating a connected system. Some lakes are upstream in this hidden network, receiving water from glacial melt at the base of the ice sheet, where friction and pressure create heat. Other lakes are downstream, receiving this water as it travels along the bedrock. And still other lakes have outflows, rivers that begin at their edges and flow toward the margins of the ice sheet, toward the coast, where this water eventually emerges into the ocean as subglacial discharge. This process of subglacial discharge is particularly significant. At certain points along Antarctica's coast, particularly beneath large outlet glaciers, fresh water from beneath the ice sheet emerges into the Southern Ocean. This discharge is not gentle or inconspicuous. The water, having been pressurized beneath miles of ice, emerges with considerable force. It rises through the ocean and creates plumes of fresh water that spread across the surface, affecting ocean temperatures, salinity, and circulation patterns. Scientists studying these plumes can detect them from satellites, watching as the cold, fresh water spreads across the darker blue ocean water, creating visible patterns of lighter color that reveal where the hidden rivers have reached the sea. In a sense, the subglacial rivers of Antarctica do touch the surface, at least briefly, before they merge into the vast ocean surrounding the continent. Scientists often describe this vast network beneath the ice as Antarctica's hidden plumbing system, and the metaphor is apt. Just as the plumbing in a building moves water to where it's needed, distributing it through pipes and channels, the subglacial hydrological system distributes water, heat, and nutrients beneath the ice sheet. Water circulates through lakes and rivers, redistributing the heat that builds up from geothermal sources deep in the earth and from friction as the ice above moves across the bedrock. This water carries dissolved minerals and nutrients that have been leached from the rocks over millions of years. And this water, this hidden circulation, plays a crucial role in sustaining the microbial life that exists in these sealed environments. The connection between this subglacial water system and the movement of the ice sheet itself is a relationship that has profound implications for our understanding of ice sheet dynamics, and ultimately for sea level rise. When scientists study how fast the ice sheet moves, they find considerable variation. Some areas of the ice sheet move quite slowly, advancing at just a few meters per year. Other areas move dramatically faster, advancing at dozens or even hundreds of meters per year. For decades, this variation puzzled glaciologists. Why would some sections of the ice sheet accelerate while others remained relatively stable? The answer increasingly lies beneath the ice. Water acts as a lubricant. When water accumulates at the base of the ice sheet, when there is a lake or a subglacial river beneath the ice, that water reduces friction between the ice and the bedrock. Ice that rests on dry rock has significant friction. There's resistance to its movement. Ice that rests on water, on a thin film of liquid water that acts as a lubricant, moves with far less resistance. This means that ice above subglacial lakes tends to move faster than ice above areas where the base is dry. Scientists have confirmed this repeatedly by mapping subglacial lakes and comparing their locations to satellite measurements of ice sheet velocity. The correspondence is striking. Where the biggest lakes exist, where the water is most abundant, the ice moves fastest. This has profound implications. If the ice sheet is accelerating, if the water beneath it is increasing, if these subglacial systems are becoming more active, then the ice sheet could be destabilizing. If it destabilizes and moves faster, more ice reaches the coast and carves into the ocean, raising sea level. Understanding how active the subglacial hydrological system is, how much water is moving beneath the ice, how fast it's moving, and where it's moving has become crucial to predicting how the Antarctic ice sheet will respond to climate change in coming decades. Will it collapse slowly or rapidly? Will sea level rise gradually or catastrophically? Part of the answer lies in the hidden networks beneath the ice, in the lubricating water that we cannot see but can only infer from satellite data and the indirect evidence of ice sheet motion. But the story of subglacial lakes takes on even more dramatic dimensions when we consider what emerges from them. What happens when the water from these sealed systems meets the surface? One of the most visually striking examples is the Blood Falls, a waterfall at Taylor Glacier in Antarctica's Taylor Valley, in the McMurdo Dry Valleys region. The falls appear exactly as their name suggests. They look like blood pouring out of the glacier. A deep crimson-red colour flows down the white ice, creating an image so dramatic and unsettling that it captured the imagination of researchers and the public alike when it was first studied in detail. For decades, the true source of the blood falls was uncertain. Scientists observed that the waterfall flowed intermittently, that it seemed to discharge at certain times of the year, and that it contained iron oxide, which gives the water its deep red colour. The prevailing theory was that the red colour came from algae and bacteria that had coloured the water as it flowed through ancient sediments. But more recent research has revealed a different story. The blood falls flows from a subglacial lake, and the water emerging from that lake carries iron and sulphur compounds derived from the ancient rocks and minerals dissolved in the subglacial water. When this water, which has been sealed in darkness for roughly 2 million years, emerges at the surface and is exposed to oxygen, the iron undergoes oxidation, a chemical reaction that creates iron oxide, giving the water its distinctive blood-red colour. Even more fascinating than the colour of the blood falls is what scientists discovered living in it. When researchers sampled the water from the blood falls and analysed it in the laboratory, they found living microorganisms. These are not the simple bacteria that might be found in most glacial outflows. These are highly specialised microbes that have adapted to an extraordinarily extreme environment. In the subglacial lake from which they came, these microbes exist in total darkness. They have never been exposed to sunlight. They survive in water that is near freezing, in an environment sealed off from the atmosphere for millions of years, in conditions of extreme isolation and stress. Yet they thrive. These microbes have evolved a remarkable metabolism that allows them to extract energy not from sunlight, as plants do on the surface, but from chemical reactions involving iron and sulphur. They oxidize minerals in the subglacial water, breaking down chemical bonds and using the energy released to fuel their metabolism and growth. This is a form of chemosynthesis, the same process that sustains life around deep-sea hydrothermal vents, where hot water, rich in chemicals, emerges from within the Earth. In the case of the blood falls microbes, the water is not hot, but it is rich in iron and sulphur, and that richness is sufficient to support a thriving ecosystem of microorganisms. The microbes are not alone. They are part of a community of organisms, a microbial ecosystem that functions entirely independent of the sun, sustained purely by chemical reactions within the sealed subglacial lake. The existence of these microbes, surviving in such extreme conditions, transformed our understanding of where life can exist. If microbes can thrive 2 million years into isolation beneath Antarctic ice, in water near freezing, without access to sunlight, sustained only by chemical reactions in the water itself, then perhaps life could exist in similarly extreme environments elsewhere. Perhaps beneath the ice of Europa, one of Jupiter's moons, where scientists suspect liquid water exists in vast oceans beneath an ice shell, similar microbial life could exist. Perhaps in other extreme environments throughout the solar system and the universe, life takes forms and strategies for survival that we are only beginning to understand. The blood falls, in this sense, is not just a dramatic natural phenomenon. It is a window into the possibility of life itself, in places we once thought sterile and dead. The scientific drive to study subglacial lakes more directly, to access the water itself and see what lives there, what secrets it holds, led to one of the most ambitious but troubled research expeditions in Antarctic science. In 2012, a British team attempted to drill into Lake Ellsworth, one of the largest known subglacial lakes, located deep beneath the ice sheet in West Antarctica. The project was remarkably ambitious. The plan was to drill through nearly 2 miles of ice, reach the water of the subglacial lake beneath, and sample that water directly, collecting microbes and water chemistry data from a lake that had been sealed for millions of years. The challenges facing such an expedition are difficult to overstate. Working in Antarctica is inherently hazardous. The continent experiences some of the harshest weather on Earth. Temperatures can plummet to far below zero. Storms arise with brutal intensity and little warning. The field season is short, only a few months during the southern hemisphere summer, when conditions are even remotely workable. The logistics of moving equipment, fuel, and personnel across the ice are enormously complex. And all of this must be done while trying to execute a technically sophisticated drilling operation that requires precision and an enormous amount of specialized equipment. The Lake Ellsworth expedition encountered severe problems. Equipment failures occurred, as they almost inevitably do in such extreme environments. The drilling rig itself encountered technical difficulties. The weather, as it often does in Antarctica, turned against the team, with storms that prevented work and damaged equipment. The window of opportunity, the brief Antarctic summer, began to close. Scientists faced a decision: continue attempting to reach the lake with equipment that was not performing as intended, or abandon the attempt and try again in a future season. Ultimately, the decision was made to halt the 2012 expedition without successfully reaching the lake. The failure of Lake Ellsworth, while disappointing to the scientific community, was not surprising to anyone familiar with Antarctic research. The continent has a way of humbling those who venture there, no matter how well prepared they are. It has a way of exacting a price for attempting to unveil its secrets. But the attempt itself, the fact that scientists were willing to undertake such an ambitious and difficult project, speaks to the importance of understanding these subglacial systems. The scientific drive to reach these lakes, to sample them directly, to understand the life they contain, is a testament to human curiosity and our desire to explore and understand even the most hidden and inaccessible environments on our planet. Beneath the water of the subglacial lakes lies another hidden world that is equally intriguing to scientists: the sediments that have accumulated at the bottoms of these lakes over millions of years. These sediments are mud, rock particles, clay, and organic material that has settled to the bottom of the water column, layer upon layer, year after year, century after century, forming a record that stretches back through time. And in these sediments lies evidence of what Antarctica was like in the distant past, before it was a frozen continent, when it had a very different climate and landscape. Antarctica was not always the frozen desert that we know today. Roughly 30 million years ago, 30 million years in the past, the continent was significantly warmer. There were forests in Antarctica. There were plants and animals that required a temperate climate. Pollen from these ancient forests, microscopic remnants of plants that bloomed in ancient sunlight, is present in the sediments at the bottom of subglacial lakes. Fossils of creatures that lived in the ancient climate are locked in these sediments, waiting to be discovered. The sediments are, in essence, a library of Earth's past, a record written in mud and minerals and preserved organic material that tells the story of Antarctica's climate history. When scientists drill into subglacial sediments and analyze what they find, they are reading this historical record. They can determine what the temperature was in ancient Antarctica by analyzing isotopes in the sediments. They can identify what plants grew there by looking at pollen. They can learn what creatures lived there by finding fossil remains. They can understand how the climate changed over millions of years, how gradually the continent cooled, how ice sheets grew, how the landscape was transformed from a temperate region to the frozen continent it is today. The sediments tell a story of deep time, of geological processes operating over millions of years, of a planet that has changed profoundly. But these sediments may be changing, may be beginning to move and be disturbed in ways they haven't been disturbed for millions of years. As the ice sheet accelerates, as subglacial water becomes more active, as the hidden plumbing system intensifies its circulation, the sediments on the lake bottoms may be stirred and mixed and transported along subglacial rivers toward the ocean. Scientists want to understand what is happening to these sediments, how they are being affected by changes in the subglacial environment, because the sediments tell them not just about the past, but about current changes happening beneath the ice sheet. The more scientists study the subglacial lakes and the vast network beneath the ice, the more they realize how much they don't know, how much remains hidden and mysterious. These lakes exist in an environment that is inherently difficult to study. They are far beneath the ice, inaccessible to direct observation. Their water and contents can only be sampled through incredibly difficult and expensive drilling expeditions. Their connections, their flows, their depths can only be inferred from indirect measurements and radar data. Scientists must piece together understanding from fragments of data, from the occasional water sample, from satellite observations of ice sheet motion, from radar surveys of the bedrock below. What makes this hidden world even more remarkable is that it exists not as a dead, sterile environment, but as a living ecosystem. Microbes thrive in these conditions. They have adapted to the darkness, the cold, the isolation. They have evolved metabolisms that allow them to extract energy from chemical reactions in the water. They form the base of a food chain that may include other organisms, though we know little about what else might exist in these sealed waters. A complete ecosystem, born and evolved in isolation from the rest of the world, maintained by chemical reactions and the flow of ancient water, continues to exist in the depths of Antarctica. Think about the philosophical implications of this hidden world. Beneath the surface of Antarctica, beneath nearly 2 miles of ice, in lakes separated from the atmosphere and the sunlight for millions of years, Living organisms exist and continue their existence in total darkness. Life persists there not because of the sun or the oxygen-rich atmosphere that sustains most life on Earth's surface, but because of the inherent chemical richness of water and rock, because of reactions that happen in the absence of light. This tells us something profound about life itself, about its resilience and adaptability, about its capacity to exist in conditions we once considered utterly incompatible with life. The subglacial lakes of Antarctica represent a kind of frontier of human knowledge. They are places that few humans have ever reached, that perhaps no human will ever directly witness, yet they affect the ice sheet that covers the continent and may influence sea level rise for the entire world. They harbour ecosystems that have evolved in isolation for millions of years. They contain sediments that record the history of a continent's transformation from warmth to eternal ice. They are reminders that even on our own planet, in places that seem barren and lifeless, entire worlds exist that we have only just begun to discover. And as you drift into sleep, as your mind grows quieter and quieter, allow yourself to imagine this hidden landscape. Picture the valleys and ridges of ancient bedrock beneath the ice, shaped by processes that occurred long before humans walked the earth. Imagine water flowing silently through darkness, moving along ancient pathways, carrying dissolved minerals and sustaining invisible life. Feel the weight of the ice above, massive and eternal, preserving these lakes in their isolation. And know that beneath your feet, beneath the solid ground you walk on, beneath the waters of the world's oceans, there are hidden places we are only beginning to understand. Worlds within worlds, waiting in darkness for us to slowly unveil their secrets. The subglacial lakes of Antarctica are among the most hidden of these hidden worlds, and they remind us that the Earth still holds mysteries, that there is still so much to discover, even in places as extreme and hostile as the frozen continent at the bottom of the world. Right now, in this moment, as you lie here listening to these words, Antarctica exists. It exists whether or not you're thinking about it, whether or not you're awake to witness it, whether or not anyone is watching. The ice is there. Millions of kilometers of it stretching across that vast white continent at the bottom of the world. And beneath that ice, in the absolute darkness, in the crushing cold, the lakes are there too. Lake Vostok, Lake Ellsworth, and thousands of others we haven't even discovered yet. They exist in silence. And in those waters, in that darkness, life continues. Right now, at this very moment, microbes are living their lives 2 miles beneath the frozen surface. They're metabolizing. They're reproducing. They're doing what they've done for millions of years, in complete darkness, in temperatures that would kill almost any other creature on Earth. This is happening right now, and you, here, in your warm bed, are part of the same living world that those microbes inhabit. You are both alive, you are both conscious, in different ways, and you are both existing in this moment together, separated only by distance and ice and time. Thank you for spending your evening with the Calm Archive. If this helped you relax tonight, subscribe so you never miss a new video. I upload regularly, and there's always something new to drift off to. Tell me in the comments, do you think there's life on Europa? Let me ask you to imagine something with me now. I want you to imagine the water beneath the ice. Picture it with me. It's down there, so far down that no light has ever touched it. No sunlight has ever reached those depths. But imagine what it's like. It's perfectly still. There are no waves, because there's no wind down there. There's no storm that could ever disturb the surface of that underground lake, because it's protected, sealed away, hidden beneath kilometers of solid ice. The water is so still that if a particle of sediment were to fall through it, it might take hours, days, or even longer to reach the bottom. It just drifts, slowly, gently, down through the darkness, undisturbed. And it's perfectly dark. Not dark like your bedroom at night, where perhaps there's a little light coming from a window, or a digital clock, or the glow of the city. This is absolute darkness, total darkness, the kind of darkness that has existed unbroken for millions of years. No sunrise will ever come to these waters. No sunset will ever colour the sky above them. The darkness is permanent, unchanging, eternal. And yet, despite this darkness, despite the cold that would destroy almost anything we know, this water is alive. Life has found a way. Think about that for a moment. Let it settle into you. In every ocean on our planet, life depends on the sun. Phytoplankton absorb sunlight and use it to create energy through photosynthesis. Fish eat those phytoplankton, whales eat the fish. Everything is ultimately powered by the sun's energy. The sun is the source of almost everything we understand about life. But here, 2 miles beneath the Antarctic ice, life doesn't use the sun at all. Life doesn't need the sun. Life has found another way. The microbes in these lakes use the energy from chemical reactions in the water, from minerals rising up from the Earth's crust from the heat of the planet itself. They don't need light. They don't need warmth in the way we understand warmth. They have found a way to exist in conditions that, to us, seem impossible, and they've been doing this for so long. For so many millions of years that we can barely comprehend the time span. They've persisted through ice ages and warm periods. They've survived while entire species have come and gone on the surface. They've endured while continents have moved and mountains have risen and fallen, and they're still there, still alive, still continuing. This tells us something profound about life itself. Life is not fragile. We often think of nature as something we need to protect, something delicate and easily destroyed. And while that's true in many ways, there's another way to think about it. Life is persistent. Life is determined. Life finds a way. Wherever there is water, wherever there is energy, wherever there is the possibility of existence, life will be there. It will find a way. It will adapt. It will survive. It will endure. The microbes beneath the Antarctic ice are proof of this. They don't give up. They don't surrender to the cold or the darkness. They simply persist, quietly, relentlessly, doing what they do, being what they are, continuing to live, moment by moment, year by year, million by year. And here's something that connects you to those microbes, that connects you to the entire story of life on this planet. You are made of water. Your body, right now, as you lie here listening to these words, is more than half water. Water is your substance, it's what you're made of. And that water came from somewhere. It came from the oceans of ancient Earth. It came from the same sources as the water in those underground Antarctic lakes. In a very real way, the same water that's been cycling through this planet for billions of years is cycling through you right now. The water in your blood might have been in an ancient ocean. It might have been in a dinosaur. It might have risen up as rain and fallen as snow. It might have been locked in ice and released again. The water is eternal. It cycles. And you are part of that cycle. You are part of the story of water on this planet. You are part of the story of life's determination to exist. This is a comforting thought, isn't it? That you are made of ancient water, that your substance is the same substance that has existed since the beginning of life on Earth, that you are connected through that water to everything that has ever lived, to the dinosaurs, to the trees, to the whales, to the microbes beneath the Antarctic ice. We are all made of the same material. We are all made of water and minerals and the energy of the sun and the heat of the planet. We are all alive in the same way, each according to our nature, each according to our needs, and we are all persisting. We are all continuing. We are all part of this vast, interconnected, beautiful thing that we call life. Imagine now what this means when we look outward, beyond our planet. Somewhere out there, in the darkness of space, there are other worlds. Some of them have ice on their surface. Some of them might have oceans beneath that ice, just like Antarctica. Europa, one of Jupiter's moons, is covered in ice, and beneath that ice, scientists believe there is an ocean of liquid water, an ocean that might be 2 or 3 times as large as all the oceans on Earth combined. And if there's water on Europa, if there's energy there, if there are the right chemical conditions, then life might be there too. Life might be living in those distant oceans right now, in the darkness, in the cold, doing what it does, persisting, enduring, surviving. We don't know. We can't see it. We haven't found it yet. But the fact that life exists in the lakes beneath Antarctica tells us something important. It tells us that life is possible in places we thought were impossible. It tells us that life is hardy and determined and creative. It tells us that life doesn't need the sun. It doesn't need warmth or light or all the things we think of as essential. Life needs water and energy, and those things might exist in places we haven't even discovered yet. There's another moon in our solar system, Saturn's moon Enceladus. It too might have a hidden ocean beneath its icy surface. Pluto has been found to have possible subsurface oceans. The more we look, the more we discover that water might be common on these distant, cold, dark worlds. And if water is there and if energy is there, then perhaps life is there too. We might not be alone in the universe. The thought of that, the possibility of it, is both humbling and wonderful. Somewhere out there beneath alien ice, there might be life that has persisted for billions of years, just like the microbes beneath Antarctica, just like us. The universe might be filled with these hidden oceans, these secret gardens of life, persisting in the darkness, unknown and unwitnessed, but no less real, no less alive. Let me tell you what it's like in Antarctica right now, at night, during the polar winter. For months, Antarctica experiences continuous darkness. The sun doesn't rise at all. It's winter night, and it lasts for months. Imagine that for a moment. Months of darkness, months of night. The temperature drops to nearly 100 degrees below 0 Fahrenheit. The wind howls across the ice at hurricane speeds. It's one of the most hostile environments on our planet. And yet, during those months of darkness, something beautiful happens above the ice. The southern lights appear, aurora australis. Curtains of green and purple light dancing across the night sky. Sheets of colour, flowing and shifting, caused by charged particles from the sun interacting with Earth's magnetic field. It's one of the most beautiful natural phenomena on our planet. Those lights dance above the ice while below, in the darkness, the hidden lakes remain cold, still, quiet. The microbes continue their work, unaware of the lights above them, unaware of the world beyond their icy prison. They simply exist. They simply are. And above them, the aurora dances. The light and the darkness coexist in that place. There's something deeply moving about that image. In the most extreme environment on Earth, in the coldest, darkest, most isolated place, beauty persists. Life persists. And above it all, the lights dance. The universe is beautiful even in the harshest places. Even in the most impossible conditions, beauty finds a way. Life finds a way. Colour finds a way through the darkness. Now, I want you to think about your own journey into sleep. What happens when you sleep is not so different from descending beneath the ice. As you drift off, as your consciousness begins to fade, you're descending. You're going down, away from the surface world, away from the light and noise and demands of waking life. You're going down into the darkness, down into the quiet, down into a place where the surface world, with all its worries and distractions, can't reach you. And that descent is not frightening, or at least it doesn't have to be. It's restful. It's healing. It's necessary. Like the microbes in their underground lakes, you need that darkness. You need that rest. You need that descent into the quiet. And there, in the darkness of sleep, something remarkable happens. Your body is restored. Your mind is renewed. The experiences of the day are processed, integrated, filed away. Your memories are consolidated. Your emotions are regulated. Your body heals itself. Cells are repaired. Chemicals are balanced. Energy is restored. In that darkness, that complete and temporary darkness of sleep, you are being renewed. You are persisting. Just like the microbes beneath the ice persist by conserving energy and finding what they need in their environment, you persist by going down into the darkness, resting, restoring yourself, preparing for the next day. Sleep is like the water beneath the ice. It's a place of safety, of quiet, of rest. It's where we renew ourselves. The water beneath the ice is perfectly safe. It's enclosed, protected, sealed away from the dangers of the world above. Nothing can disturb it. Nothing can harm it. It's deep and dark and safe. And in that safety, life thrives. Life continues. Life is restored and renewed. When you sleep, you're entering a similar sanctuary. Your bed is your shelter. The darkness around you is your protection. The quiet is your sanctuary. And in that safe place, you are renewed. Your body, like the water in the Antarctic lakes, needs this sanctuary. It needs this darkness. It needs this peace. Think about the temperature of those underground lakes. It's cold, yes, far colder than the human body, but it's consistent. It doesn't fluctuate. It remains steady day after day, year after year, million after million of years. That consistency is what allows life to thrive. The microbes have adapted to that specific temperature. They've evolved to function perfectly in that cold. And because the temperature never changes, they never have to adapt further. They can just exist. They can just be. When you sleep, your body temperature drops slightly. It changes from your waking temperature to your sleeping temperature. And as your temperature drops, as your body begins to cool, you should feel yourself becoming more relaxed, more at ease, more ready to sleep. Your body is preparing itself for sleep. It's following a rhythm that's as old as life itself. The rhythm of activity and rest, warmth and cool, waking and sleeping. This is natural. This is right. This is how you're designed to work. The comfort of your bed, the warmth of your blankets, the cool of your pillow, the darkness around you. These are all signals to your body that it's time to rest. Your body recognizes these signals, and like the microbes in their cold, dark, safe environment, your body can relax. It can settle. It can persist in the way it's meant to persist. It can rest. As you continue to listen to these words, let yourself sink deeper. Let yourself descend like you're going down beneath the ice, down into the darkness, down into the quiet. Let go of the surface world. Let go of your thoughts and worries and the things that occupy your mind during the day. They don't belong here. This is a time for rest. This is a time for your body to recover and your mind to quiet. Imagine yourself going deeper, deeper, down into the peaceful darkness. And as you go deeper, imagine that you're becoming like those microbes, perfectly adapted to your environment. You belong here. This darkness, this quiet, this rest. This is where you're meant to be. Your body knows how to be here. Your mind knows how to rest. Just let it happen. The water beneath the ice has been there for so long that it's become eternal. Time moves differently in those depths. 1,000,000 years is just a moment in the grand scheme of the planet. But for the microbes living there, for those simple organisms, each moment is real. Each moment is their entire world. They don't think about time the way we do. They don't worry about the future or regret the past. They simply exist moment by moment, doing what they do, being what they are. There's a kind of peace in that, a kind of freedom in simply being, in simply existing, in simply continuing. As you drift towards sleep, try to adopt a similar perspective. This moment right now, as you listen to these words, is your entire world. There's nothing else. No past to worry about, no future to fear, just this moment, just the darkness, just the quiet, just your breath, just your heartbeat, just the gentle sound of my voice, like water moving through darkness, like the slow, patient work of life in the depths. Let this moment be enough. Let this be sufficient. Let this be everything you need right now. There's no judgment in that underground world, no comparison, no hierarchy. The microbes don't worry about whether they're successful or whether they're living their best life. They simply live. They simply do what they're designed to do. And in that simple existence, there's a kind of perfection, a kind of peace. As you lie here in your warm bed in the darkness, let yourself exist in that same way. Don't judge yourself for resting. Don't feel guilty for taking this time. Don't worry about whether you're sleeping right or well enough. You're doing what your body needs. You're following the rhythm that's written into your very cells. You're persisting. You're continuing. You're alive. That's enough. That's perfect. The hidden lakes beneath Antarctica have existed for millions of years without anyone knowing about them. They didn't need to be discovered. They didn't need to be studied or understood or acknowledged. They were just there, just being, just continuing, and they were perfect in that unknownness. There was a kind of beauty in their hiddenness, a kind of peace in their isolation. You don't need to prove anything to anyone right now. You don't need to accomplish anything or understand anything or achieve anything. You just need to rest. You just need to be. You just need to exist in this moment, in this darkness, in this quiet. Let that be enough. Let that be your entire purpose for the next hours, to rest, to sleep, to be, to persist. As you sink deeper into sleep, deeper into the darkness, imagine yourself in that water beneath the ice. You're surrounded by cold that's gentle, not harsh. You're in absolute darkness that's safe, not frightening. You're in perfect stillness that's peaceful, not lonely. Around you, life continues. Life persists. Life endures. And you are part of that. You are part of this vast, interconnected living planet. You are part of the story of life's determination to exist. You are part of the water cycle. You are part of the continuity of life. And right now, in this moment, you are resting. You are being restored. You are being renewed. The scientists who discovered the lake beneath the ice did so with a sense of wonder and reverence. They understood that they were glimpsing something ancient, something hidden, something that had existed in mystery for millions of years, and they treated it with respect. They treated it with care. They understood that this lake was precious, that this life was precious, that this hidden world was worth protecting and understanding. Treat your own rest with that same sense of reverence. Treat your sleep with the care and respect it deserves. Your body's need for rest is not a luxury. It's not something you should feel guilty about or rush through. It's essential. It's sacred. It's as important as the hidden lakes are important to our understanding of life on this planet. Your sleep is important. Your rest is precious. Your body is precious. And you deserve the care and comfort you're giving yourself right now. The night is always there. Even when you're awake during the day, the night is there, on the other side of the planet in the darkness waiting for you. And the hidden lakes are always there too, beneath the ice, continuing their quiet work, persisting in the darkness. The world is always working, always continuing, even when you're not watching, even when you're not aware. You can trust in that continuity. You can trust in the persistence of life. You can trust in the rhythm of day and night, waking and sleeping, activity and rest. And as you continue to listen to these final words, let yourself fully surrender to sleep. Let yourself fully accept the rest that your body's asking for. You've earned this rest. You deserve this rest. The day is done. The world continues without you, and you are safe here, in your bed, in the darkness, in the quiet, surrounded by everything you need. You are warm, you are safe, you are comfortable, and you are at peace. The story of the lake beneath the ice is your story. The story of life's determination to exist is your story. The story of persistence in darkness is your story. You are alive. You are continuing. You are enduring. And right now, in this moment, you are resting. You are being restored. You are being renewed. And as you drift deeper into sleep, as your consciousness fades and you descend further into the darkness, know that you are safe. Know that you are cared for. Know that you are part of something vast and beautiful and eternal. And so, as the Antarctic night falls around the hidden lakes, as the aurora dances above the ice, as the microbes continue their ancient work in the darkness below, I hope you find your own rest. I hope you find your own darkness, your own quiet, your own peace. I hope you descend into the sleep that you need, into the restoration that your body is asking for, into the sanctuary of your own quiet mind. Thank you for joining me on this journey beneath the ice. Thank you for listening to the story of the lake and the microbes and the persistence of life. And thank you for allowing yourself to rest, to sleep, to be restored. You've done something beautiful tonight. You've taken the time to care for yourself. You've allowed yourself to slow down, to quiet down, to rest. Sleep now. Let the darkness wrap around you like that cold, safe water. Let the quiet settle into you like sediment slowly falling through the depths. Let your body do what it was designed to do. Let yourself persist. Let yourself endure. Let yourself be renewed. And when you wake, you'll be ready. You'll be restored. You'll be renewed. Just like life beneath the ice, just like the hidden lakes, just like the microbes that have persisted for millions of years. Good night. Rest well. Sleep peacefully. And dream of the beautiful hidden world beneath the ice, where life continues, always in the quiet and the dark and the cold. You are safe. You are cared for. You are at peace.